Alright, howdy y'alls. It's the Diabolic vTutor, and we're resuming activities from last time. Last time we were we were beginning to factor polynomials. We basically got through the introduction of long division. It's a pretty long algorithm, of course. And we're going to be talking about the streamlined algorithm, the streamlined version of long division, which is just going to be synthetic division. And then we'll also be doing some practice problems with that one. So hopefully we're going to be doing a good amount of practice problems. Alrighty. So I guess we had to start off with a little bit going backwards. If you haven't seen the first one, that's fine. But suppose we have some sort of polynomial. I'm going to write out the answer first. It's going to be in fully factored form. I'm going to distribute the factors and then generate the problem from those factors. So we'll have the answer in front of us ahead of time. We're going to have a polynomial p of x. And this polynomial is going to consist of these factors. There's going to be a 2x minus 1 times x minus 3 and times an x plus 2. So again, this is the answer that we want to eventually get to for purposes of probably setting it equal to 0 to find the solutions, but not major concern at the moment. We're just going to distribute this one. This one is the familiar quadratic portion. This whole factor here becomes a quadratic, so if you distribute, it's going to be x squared, and then negative 3 plus 2x is going to give us negative 1x. Negative 3 times 2 is going to give us negative 6. That is distributed. Now we have this portion here. It's going to be a 2 by 3 distribution, so again, foiling will fail in this situation. So just keep organized. First times first. First times first. First times second. First times third. Finish with that one, and then second times first. Putting it in stacked. Second times second. Make sure your signs are correct. And then second times third. So we have 6 terms, which is correct because 2 by 3 expansion, you're going to give it 6 terms right off the bat. Before combining like terms, now we combine like terms. There is the problem. And again, just pay attention to where things are coming from. We have the 2x times the 1x times the 1x, and those ones contribute to generate this particular term right here. We have constant times constant times constant. Those 3 constant. The product is this ending constant. So those 2 terms are the easiest ones to trace. This one is easy to trace, and then this one is easy to trace. The middle 2 terms, a little bit more difficult to trace, especially when you are trying to factorize. So again, this is the full work. The answer is here. If we were trying to factorize p of x, we're going from this bottom portion to the one I'm shaking right now, the 2x minus 1 times x minus 3 times x plus 2. That's what we want to get in the end. So I'm going to take this trinket, hide it behind my back. You can still kind of see it. That's perfectly fine. So here is the problem. There we go. We wish to come up with the candidates because, again, we're trying to factorize this. The detective work is a little bit more difficult because of the higher degree of guess and check versus, in contrast with the quadratics, where the detective work is a lot clearer and then you can get the definite answers a lot faster. There's very little guessing game because most of it is the numbers make a lot more sense. So this one, we have to first come up with our candidate. we know if this is a design problem, then we know that we can get a factor out of this. It will be this factor that we can get out times the remainder. And just as a reminder, if you have something like a value of 8, if you suspect that the factor is 4, one factor, no, let's not do 8, let's do 6. Because I like 6, as it consists of prime factors that are unique. So this one, you suspect that 6 is here. If you suspect that one of the factors of 6 is 3, for example, can we divide 6 by 3? Yes, there will be 2 3's that fit into 6. So you subtract that, you get 0, remainder 0. So key point, if something is a factor of another number, then that something, if you try to divide that number by something, you get a remainder of 0. And this other thing that you got, I think it's called the quotient, that thing is another factor of the larger number. Whether or not you can break this down is a follow-up question. But as you see, we have two things. We have red factor times blue factor gets you back to the original scenario. So this was right here, we're trying to figure out what is that first red factor. So in order to determine the red factor, we have to do a little bit of breakdown work. So we have to figure out the factors of 6. Factors of 6, 1, 2, 3, and 6. Factors of the leading coefficient, 1 and 2. Again, we're choosing those ones because it's clear, it's a lot easier to figure out where this 2 and where this 6 came from than it is to figure out where this -3 and -11 come from. So put a plus or minus, and these are all our possible numbered candidates. We can have a 1 over 1. That's positive. That could be a candidate as a 0 for our function. So the function simplifies into +1. If this is your candidate, if you believe this is a 0 of the function, we can transform it into a factor candidate. It will be x minus 1. Because again, why is this called E0? Because if you plug it in here, you get 1 minus 1, which is 0. And if that factor produces 0, 0 times the rest of the factor is going to be 0. This is why this is referred to as a 0. And zeros will easily lead you to factors because they're interrelated. They're almost synonyms. They're not synonyms, but they are almost synonyms. Just because they're tied so closely together. So we suspect that this is a factor of this particular function p of x. To check whether or not it's a factor, we're going to do long division. This is if we don't have synthetic division. So here is x minus 1. We're trying to divide the p of x by x minus 1. So we're going to use these ones to populate. We have 2x cubed minus 3x squared minus 11x and then plus 6. So is this a factor? Remember the procedures. How can we get this to match this one as much as possible? It's going to be 2 squared. So we need to multiply by 2x squared. So if we choose 2x squared, it will multiply to this one, and that's what we are subtracting from this portion right there. Because this is analogous to long division from what you've learned back in the days. I know I covered it in the other stream, but I wish to reinforce this idea. So if you have 2, and you're trying to determine if 2 is a factor of 2,436, for example. You're trying to determine if 2 is a factor. You can just do the long division. How many 2's fit into this 2? 1 will fit into it. So minus 2. You drop the 4. How many 2's fit into this 4? There'll be 2 of them because 2 times 2, if you subtract it, will give you 4. Producing 0. We're going to finish the rest of it. Drop the 3. How many 2's fit into 3? 1 of them will fit into the 3. So I'm running out of space right here. Bad habit. I always start writing. I should write right way up there. Okay. So again, you drop the 3. How many 2's fit in this 3? Only 1. So minus 1 times 2 gets you here. So 3 minus 2 is 1. You drop the 6. So we have 16. How many 2's fit into the 16? It'll be 8 of them. 8 times 2 subtracted from the 16. It happens to be 16. So we get 0 from the subtraction. So we have, what does that 0 mean? It means that we have a remainder of 0. So when you have a remainder of 0, that means this number in question is indeed a 0 because it produced a 0. Great naming scheme, right? So because this 2 is a 0, this 2 leads to a remainder of 0. It is therefore, by definition, a factor of 2,436. So that is the basis of what's going on when we're doing this long division, except we have the letters to contend with, but the idea is exactly the same thing. We're trying to fit these ones into this thing right here. So long division. So this one times this one, we're going to subtract it from the corresponding like terms. So multiply this times x gets 2x cubed. This one times negative 1 gives us negative 2x squared. But remember this subtraction always, because we're trying to figure out what do we have left after fitting this many x minus 1's into these two positions. Alright, do the subtraction. This one cancels perfectly with that one because that's by design. We intended to do that. And this one minus minus, which is plus. So we have leftover x, negative x squared. Drop down the negative 11x. We ask ourselves again, what times this x produces this exact same thing? It's going to have to be negative x. So this one times this one. You subtract it to see how much do you have left over. So after fitting this one times this one, we're going to get minus x squared and then plus x. So we have the minus parenthetical yet again. So this one minus minus is plus, so these two perfectly cancel. This one minus positive gives us negative 12x. Finally, drop the 6. So what number needs to be here to multiply with this to make it exactly match this one? It's going to be negative 12. So do the math. And then this one times that. Positive 12. So we have a subtraction going on because that's the way the long division works. So this one minus this one cancels perfectly. This one minus 12 gives us negative 6. So we have a remainder of 6. What does that mean again? Because we have a remainder of 6 when we're trying to divide our polynomial. We're trying to divide our polynomial by x minus 1 as a factor. We get a remainder of 6. So because we have a remainder of 6, this is not a factor. So, not much to do. So we did all this work to rule out this positive 1 candidate as a factor. So the 1 cannot be a factor. The 1 is not a 0, so x minus 1 is not a factor of p of x. Does it seem like a lot of work? Yes, it is extremely tedious. So that is the long form. This is long division, so it's living up to its namesake, certainly. So this is where synthetic division comes into play. Synthetic division is the exact same thing that we're doing right here. It's just more streamlined, so you don't have to write all the x terms. And by keeping the notation shorthand, you can go through the algorithm a lot faster than to do this whole chunky thing. So here is the corresponding synthetic division root. So you see how this is a factor, right? We got this factor because we hypothesized that maybe 1 is a 0. But in contrast, when you are doing synthetic division, the one candidate that you were considering as a 0, you just put that directly into your synthetic division. So it goes like this. There is a 1. That's our candidate. We suspect that this is a 0 for our function. And then we populate this portion here with the coefficients and the constant of our polynomial. So we're going to get 2, we're going to get -3, we're going to get -11, we get +6. What exactly are we doing? We're doing the exact same thing as long division. So you see how this 1 here is a 1 there. This 2 here is just a 2 there. This -3 is just a -3. And then this -11 is this one, and then the 6 is this 6. So are we doing anything new? No, we're not doing anything new. We are simply writing things, but omitting things that are visually not completely needed. All right. And here's how this engine, this algorithm works. We are going to add this straight down. There is no number here, so you just add straight down. It is a 2. What does this mean? It's just simply the 2 right there. So that's not a big deal. So what we're going to do is we're going to take this 1, we're going to multiply it to this 2, and that's the number that ends up right here. So we're going to get 2. We're going to do the exact same thing as we did in the prior step, in which you just summate downwards. So we summate directly downwards. So -3 plus 2 is -1. And this one, what is that doing? This one is actually just this -1 coefficient right there. So do we have to write all this nonsense? No. Because it's unnecessary. This is part of the machine. You trust in the mechanics of the machine to get you the right answer. But ultimately, this machine is doing the exact same thing as this long division. So we have -1. We're going to continue with this algorithm. So same procedure. You take this 1, multiply it to this -1. You get this number right there, -1. And we're going to summate those two straight down. So -12. Where does that correspond to for our long division? You can, again, hopefully you can see it. This is a -12. That's the same -12 that you got here. Where did you get that -12 from? By summating -11 and -1, which is right there and right here. Is this a negative? Yes, because of the mechanics of long division. So negative, +1 is -1. Alright, and then of course, lastly, we are going to do the final step. This -1 times this one gets this particular number. -12, you summate straight down, and then you get a -6, which again should feel very familiar. Where did this show up in the long division corresponding side? It's right there. That's where it came from. How did we get this -6? By summating the 6 and the -12. That's the 6, and that is the -12. Right there. So again, we're not doing anything special. This is not a new method. This is just simply a streamlined version. Look how compact, look how nice and compact it is, and look how fast we were able to execute it. So just follow this algorithm very mindlessly, but understand that it's just a shorthand notation for long division, but it's only exponent 1. However, if this is exponent 2, this one, you can't translate it directly into this one. You need to jump through a few more hoops to do it. So there it is. So the entirety of the long division we can symbolically represent with less notation, and we could do it a lot faster doing it in this particular fashion. But the result is the same thing. We got a remainder of 6. Isn't that just a remainder of 6? And because this remainder is -6, did I say 6? I mean -6. And because this is not a remainder of 0, we can therefore conclude that this is not a 0. Because if +1 was a 0, it would have resulted in a 0 remainder. So going backwards, then 1 is not a 0. It has failed as a candidate, so we can try another one. Isn't that fun? So let us delete that. Let us delete that. Let me rewrite these zeros. 0 candidates. So we have 1, 2, 3 and 6 are as potential candidates in conjunction with this 1 and the 2. Again, these factors came from factorizing the 6, which feels like it's akin to factoring quadratics. And then those two came from the 2. Plus or minus, because we have multiple signs to deal with as well. So this one is a candidate of 1, or it could be negative 1. We already wrote out positive 1, so let's try the answer that I can see from right here. So you can't see it, but I can see it, so it's going to be 3. Let's just show you the long division first. So suppose we luckily guessed 3 as a 0 candidate. So let's do long division first, just to review. So if 3 is the 0, then from that 0 we can produce the factor candidate, which is x minus 3. Because again, 3 minus 3 gets you 0. This is where this name comes from. So we're trying to figure out if x minus 3 is a proper factor. We will do long division by dividing p of x by x minus 3. So here we go. Look how much I have to write. So I have to write this junk, I have to write this junk. And I'm just going to speed run this entire process. So we're going to have perfect match is going to be 2x squared, so minus. Now it's a good time to practice your long division. Multiply. Form the subtraction. Watch out for sign shenanigans. You drop down this negative 11x. We need to match this perfectly. Sometimes this one yields here. Minus 9x. Perform the operation. Minus is plus. Drop down. Perfect match. Negative 2 times this one. Bring it here. It's going to be negative 2x plus 6. Parenthetical close. Perform the operation. Subtraction is 0. 6 minus 6 is also 0. Perfect. This is good. So again, the fact that it equals 0, we get a remainder of 0, or the fact that we got a 0 means we have a remainder of 0. A remainder of 0 means that this one actually is a factor of p of x. And that's it. So let's do the corresponding synthetic division. Again, contrary to what long division does, we don't need to convert this into a factor. We leave this 3, 0 as it is. So that's our 3 as a 0 candidate. You're going to copy all these coefficients, because we're just writing this part right here. So it's 2, negative 3, negative 11, and then positive 6. Again, always sum straight down. So 2 plus nothing is 2. 2 times 3, 6. Summate straight down. Form the algorithm yet again. So when you take this and you multiply to this one, it's just doing this. It's just doing this. What is it doing? It's doing 3 times this one to get this one. So again, all of these are analogous. The action that we are performing here is the same thing that is happening right there. Exact same motions, exact same mechanics. It's just we're writing less stuff. Alright, so again, take this, multiply to here, summate. Lastly, summate straight down, we get 0, and that's exactly what you want. The fact that you have produced 0 means that that 3 is a 0, which means this is conclusive. Because 3 is a 0, then x minus 3 is a factor. Factor of what? The polynomial p of x. And then we're done. Look how much faster that was. If you count the time that took me to write this out via synthetic division is a lot faster than fully writing it out. So please, if you can use synthetic division, please use synthetic division. It basically only works if you have exponent 1. Otherwise you have to tweak it quite a bit. So we're done with one factor. So we have figured out that, again, x minus 3 is a factor of p of x. But what are these other numbers right here? This other, oh, I shouldn't have deleted it. Hold on, let me move. So same conclusions as before. Let me just clean things up a little bit. So look at the numbers here. We have, this is 0. But what are these other numbers you're doing? If you look on the corresponding long division, this 2 here corresponds here. 3 corresponds there. Negative 2 corresponds here. This is the leftovers. This is a leftover factor. That's the red thing, right? And then this is the red factor. So it's going to be red factor times blue factor equals what? The entirety p of x. Again, I wish to draw these. I'm probably reiterating this too much, but 3 factor times 2 factor gets us 6 factor. It's that. It's just that. It's just that. What's the blue factor? It's these things right here. It's that thing right there. So this is just 2x squared plus 3x minus 2. Red factor, the one we just figured out, is x minus 3. Alright, let's do a little bit of cleanup at this point. So let us delete all that. That's our conclusion so far. And then if you take a farther look, isn't that just a quadratic? So let us factorize that quadratic. Ooh, it has a coefficient in the front, so that's always annoying. We have 2x squared plus 3x minus 2. Don't forget your factoring methods. Factoring of this one is 2, 1. Factors of this one also 2, 1. In what combination can we get a positive 3 in the middle? It is 2 times 2 is 4. And then 1 times 1 is 1. If you subtract those two, you get 3, which is exactly what we want. So let's generate the factors. The factors must be this 2 here and this 1 here, or how you produce this one. So that is a 2x, and this 1 here is the 1x. And then these ones in the back is how we produce this negative 1 constant, this 2 here. What's happening to this 2? We're multiplying the 2x to that 2. So the 2x has to be multiplied to the 2. There it is. And this 1x, that's this one right here, has to be multiplied to 1. That's to this one. Signages, the two signs are different. The larger the 2 is positive. So this is 4x, which is larger than 1x. So the larger magnitude needs to be positive, and then the smaller product needs to be minus. That's it. So that is the factored form for that quadratic. Let's write it out. So that is fully factored form. This is just x power 1 minus 3, and this is also x power 1. This is also x power 1. So this is referred to as fully factored form, the triple F's. It's kind of fun saying it, fully factored form. FFF. There you go. And we have successfully fully factored out p of x, and we are done with this particular problem. We can get to graphing another time, but let's not dwell on it for now. So that is using the quadratic algorithm. Could we have used synthetic division on this? Yes. So let me show that again. So using the 3 again, starting way from the top, what are the coefficients of this one? Using the first candidate, which we already know works out. Drop that multiply, sum, multiply, sum, multiply. 0, perfect. That's what we want. You can continue this, you can chain to the negative division of this one. So what are the candidates of 2 and 2? Well, don't use these guys anymore, because this is strictly the candidates for using this 6 and this 2. We now have different candidates for the next round of synthetic division. It's these factors over those factors. So just 2, just 1 and 2 over 1 and 2. Are we going to try 1? Don't try 1. That has already failed as a candidate. If it failed before, that was the first one that we tried. If it failed then, it's still going to fail now. So don't pick positive 1 yet again. I'm gonna cheat and just use one of the answers that I could visually see right there. So if you choose a candidate, let's not cheat that much. Let's use -1. So if we suspect that -1 is a 0, then we put it straight down as -1. Okay, remember, you don't need to convert this into a factor. Convert it to a factor will be x plus 1, which you would use for long division. But this algorithm, synthetic division, you don't need to convert it into a factor first. So let's execute the steps. Drop the 2. Multiply. Sum. Multiply. Sum. And the fact that we did not produce 0 means this is not a 0, which means x plus 1 is not a factor. But we already know that because we already did the problem. And then now if we got lucky and we selected positive 3, I'm sorry, not positive 3, -2, what would have happened? Drop that down, multiply, sum, multiply, sum. There it is, the 0 that we desire. The fact that we got a 0 here means that -2 is a 0, which again, translated, means that x plus 2 is a factor. In conjunction with the 3 up there, which is a 0, that means x minus 3 is also a factor. What are these leftovers? The leftover is actually 2x minus 1. So that's our third factor. And then we're done. This one is a little less efficient. Once you hit the quadratic situation, just use whatever method you like best. Personally, I don't like to guess and check. So I would go with the tried and true quadratic algorithms that we already have at our disposal. So why waste time? But I'm just showing you that the synthetic division, you can continue on with it. It is you would chain synthetic division if this is greater than 3. You know, if you don't end up with a quadratic, you have to keep going with the synthetic division, and it becomes extremely tedious. But let's backtrack just a little bit, and I'll show you how to deal with the fractional 0 guess. So what if we did not guess -2? There are some other guesses that we can perform, like other candidates to check. So starting from here, what if we chose 1 over 2 as our candidate? This is our 0 candidate. So again, you don't change that into a factor, you just put it as is into the synthetic division algorithm. So drop the 2, multiply, sum, multiply, sum, and then you produce a 0. That's very nice. Alright, so what does this mean for us? It means that this 1/2 is actually a 0, and because it's a 0, you can convert it into a factor. And I'm just going to keep reiterating that the factor is x minus 1/2. Put that together with the 3, and the 3 as a factor becomes x minus 3. Okay? And now, at this stage, it might look a little, just a tiny little strange. So let me unhide the answer from behind my back. Here's the answer. The complete answer. That's what we have so far. You can see that the x minus 3 agrees with this x minus 3. That's no problem. But what is this? This is an x minus 1/2. That's kind of distinct from 2x minus 1. Right? Like, wait a minute. Isn't that some sort of discrepancy? You can see that putting in 1/2 here, 1/2 minus 1/2 is still 0. And if you plug in 1/2 here, 1/2 times 2 is 1, and 1 minus 1 is also 0. So at least the definition of the 0 holds true. But what gives? It looks kind of weird. So can we trust this is the answer? And yes, because look at the third factor. Look at what this thing right here is. It's actually 2x plus 4. But I should explain this one a little bit. Remember, this is an artifact from long division, and the terms have been omitted. The x portions have been omitted, but if you track this in long division, if you just had done this entire thing through long division, you would see that this is going to be 2x, and this will be positive 4. Okay? And I'll ask you to trust me on that, but if you don't trust me on that, here is the reasoning behind it. We started off with a cubic function. Once we have done the first syntactic division, we are essentially dividing by x minus 3. So if you divide cubic by singular x with an exponent of 1, you reduce the power by 1. So it will become exponent 2. This is a result from the first syntactic division. And then if you perform the second syntactic division, we are dividing that one, at least in part, by x minus 1/2. So when you do that, this exponent downticks by 1, thereby becoming exponent 1. And this is just the coefficient that accompanies it. And this is the other piece that's left over. Okay, so this is going to be 2x plus 4. You can, I promise you, you can do the long division to verify that, but I'm kind of lazy at the moment. Okay, so having said that, this is now going to be 2x plus 4, which we can copy paste right here. So is this answer the same as that answer? And yes, because this one is factorizable. You can factor a 2 out from both of those. So divide by 2, divide by 2. What do we do with that times 2? You can beautify the first factor by distributing the 2 into the first factor. So if you distribute a 2 into this one and this one, we're going to get 2x plus 1. The x minus 3 is unchanged. So at this point now, this is perfectly a visual match for this one. So yes, it is synonymous. The annoying thing dealing with fractional zeros is that you're going to get factorizable end products, but you just bring out the most common factor, the greatest common factor. And you could use that greatest common factor, and you could re-multiply it back out to change this into a non-fractional value. It's just for beautification purposes. You're not technically wrong, but I think you would be deducted points if you left it like this. Okay, so that's that. We're gonna just run through some problems, maybe 2, 4, 6, 8, 9 problems. Maybe 9 problems, but let me first generate another problem on the spot. I have 9 pre-written problems. I want to bring it up to a nice perfect 10 after the first tutorial. So let's do h of x. So I'm going to already have a quadratic in my head. Here's the quadratic. Here's the quadratic that I have is going to be minus 20 here. Factors of 20. Then I want to select 10 and 2. 10 and 2. So we get negative 8x. So that's factor number 1, which again, that's just a quadratic. Then factor number 2 is going to be right here. I'm going to be, let's do simple, 2x minus plus 1. Alright, so again, this is part ways to the answer. This is a 3 by 2. Let us do distribution. If we do a 3 by 2, we're going to get 6 terms. So, good review of distributive property. We're going to do first one to first. So, 2x cubed, first to second. We are finished with the first term. That's done. Distribute second term to first. And then second term to second. And notice how I'm stacking my answer. It's just for visual clarity. You don't have to do it. Negative 20 times 2x. Negative 20 times 1. See how this nice staggered? You could just add straight down. There it is. We have the problem successfully generated. I'm going to take this one, shrink it and hide it. Alright, so here's the problem. Always, always, always double check to see if you could factor something from all of them. But the way I designed the problem, you can't factor something from all 4 terms. So we're going to jump straight to generating the candidates for the zeros. And remember, all these numbers have come from somewhere, but the ones we pay most attention to is the last one and the first one. Technically, these ones are informative, but they're a lot harder to deal with. So factors of 20, 1, 2, no 3s, 4, 5, 10, and 20. So there's a sort of symmetry going on. This one times this one is 20 times is equal to 20 is equal to 20. So that's how you keep track of everything. Making sure you have all the factors. Those are the factor candidates of negative 20. Don't forget to put plus or minus. Those are the factors of 2, just 1 and 2. So we have a bunch of candidates. Again, this is how you read it. Here is one candidate, but it can be plus or minus. So plus or minus 1 is a possible 0 candidate for this polynomial. This one is also a candidate. So plus or minus 2. This one, 2 over 2, is 1. We have already written that candidate. So you can see how you can kind of get annoying keeping track of all the candidates. But 4 and 1, 5 over 1, 10 over 1, 20 over 1. And have we missed anything? Yes, we've missed the fractional, so we could have 1 over 2. 2 over 2 is 1, we already have that. 4 over 2 is 1. 4 over 2 is 2, we already have that. 5 over 2 is something novel. 10 over 2, we already have that. We already have that one. So those are all our possible candidates, and remember, just like what we had seen with quadratics, not all candidates are created equal. Some of them are usually more likely picked than other ones. In particular, the fact that this is a negative 15 and a negative 48, we can rule out the extreme values like 20, plus or minus 20, or plus or minus 10. So they're not as many candidates as it might initially seem. So don't pick the extreme values. Pick typically the ones that are closer to 1, especially when you're starting off. Again, the coefficients aren't steamrolling very quickly. So what are we going to pick? Most people choose 1 or negative 1, so why not just pick positive 1? We're not going to do a long division at this point because it's inefficient. So just take the coefficients from each of those to populate the algorithm. So we have 2, negative 15, negative 48, and then negative 20. Signage is very important. It does pay to double check to see if your signs are correct. Otherwise your work will be for naught. Follow the algorithm. Sum down, multiply, sum down, multiply, sum. We could stop here. And here's the reason why we could stop here. If you summate those two, you get a very large negative value. If you multiply 1 times a negative, you result in a negative here. That's not going to get you 0. But we will keep track. Actually, no intermediate value theorem. Okay, so ignore what I said. So we're not doing intermediate value theorem, so we're not going to keep track of this one. But let me just do the full work. So summate, we get negative 61. Multiply. This is a negative 81, which again, it's not 0. Because this is not 0, 1 is not a 0. Because 1 is not a 0, x minus 1 is not a factor. So, done with that. 1 is done. 1 and done with the 1. Absolutely riveting, is it not? So 1 has failed as a candidate, but what about negative 1, right? Here we go again. Just populate the chart. We have 2. I should not erase the entire thing, but that's okay. There they are. Drop the 2. Multiply. Sum. Multiply. Sum. That's bad. This is a positive 31. Summate those. That's clearly not 0. Which means negative 1 has failed as a 0 candidate, which means x plus 1 is not a factor. So this 1 has been completely eradicated. It's gone. There's no more. But there is something very, very interesting. The negative 1 here resulted in a positive 11 remainder, but then the positive 1 as a 0 resulted in a negative remainder. And now I'll talk about intermediate value theorem in short. Because one of the remainders is positive and then the other remainder is negative from those 2 0 candidates, that implies that there is a 0 between those 2 candidates. So between 1 and negative 1 as zeros, there lies a 0 candidate that we need to test. Okay, this is going to be I'm going to elaborate this when we actually get to graphing in regards to why this intermediate value theorem works. But between 1 and negative 1, there is a 0 because we have a negative remainder here and a positive remainder right there. So there must lie a 0 between this positive value and this negative value. You don't have to memorize this, especially not now, if this is new to you. You can just continue testing whatever numbers you wish, but please don't pick the extreme values. It's going to be almost always a waste of time. Okay. But because of what I've just said, if you take me on my word and you truly believe that there is a 0 candidate that is the right one between negative 1 and 1, well, what number is between negative 1 and positive 1? None of those, and not this. So only plus or minus 1/2. So let's test one of those. So let's test positive 1/2 first. So if we suspect positive 1/2 is a 0, you just need to go through the motions yet again. Are you tired of this yet? There's like 10 more to go. Alright, it only gets worse. So drop the 2. Multiply. Sum. Multiply. Sum. Technically you can stop here because you see you're going to get a negative right here. Negative plus negative is not 0. So this one is not a 0, but for completion's sake, I'm just going to do the entire thing. Oh, this is bad. That's a negative 55 over 2. That's unpleasant. This is going to be negative 40 over 2. Summate that, you get negative 95 over 2. Again, the fact that this is non-zero means this is not a 0. That's not a factor. Okay. So our first candidate between negative 1 and positive 1 has failed. So what has failed so far? Negative 1 as a candidate has failed, 1 has failed, and then positive 1/2 has failed. So the only number left between negative 1 and positive 1, as dictated by the intermediate value theorem, is negative 1/2. So this one had better give us a 0 after doing the synthetic division. So final run, I promise. Number 1, because remainder factor theorem, intermediate value theorem guarantees it. And number 2, I could see it literally right here. That's the answer. Alright, let's do it. So we have 2, negative 15, negative 48, and negative 20. Sum, product, sum, product, sum, product. Perfect. We have a negative 20 plus positive 20. That yields 0. Isn't that nice? Because we have finally gotten a 0, that means negative 1 over 2 is a 0, which means we can convert that into the factor. A factor of h of x, which is x minus 1/2, which is plus 1/2. So it looks kind of funky because there's a number that's a fraction inside the parenthetical. You can see that the remainder here, this is the, not the remainder, this is the quotient. The quotient is 2, -16, -40. But remember, this is shorthand notation. There are actually x's attached to each of these. What are the x's? Well, we start off with x cubed. We divide by x power 1. So by exponential rule, 3 minus 1 is 2. So 2 is the coefficient for x squared, and then -16 is a coefficient for just x. And -40 is a coefficient for x power 0. And remember, x power 0, that's just 1. So that's all we have. So let's clean up just a little bit just to see where we're at. I wouldn't show this part when I'm doing this problem though, so copy paste this. If you can see it, this is an even number, and even number. Because they're all even numbers, the GCF is also 2. So we can factor out the 2 from those 3 terms, thereby yielding x squared minus 8x minus 20. We now have 3 things multiplied together. We can take this 1 here, beautify the first factor by distributing it to half and to x. And finally getting a much cleaner situation of 2x plus 1 times x squared minus 8x minus 20. And are we done? This is one factor. Yes. This one is a quadratic, so you have to use your quadratic tricks. Or you should use your quadratic tricks to factor out this one. Again, you can continue to use synthetic division on this one. You can chain combo it off here, asking, what is this one? But that's too much guesswork for my tastes. So jump straight to the more surefire method. Factors of 20, that sums to make 8. Or let me repeat that. Factors of -20, that if you sum 8 makes -8. So factors of 20, 1 and 20, nope. 2 and 10, that looks correct. 2 and 10. So I'm going to put 10 arbitrarily here and then 2 arbitrarily there. The negative means that they have different signs. The sign here is opposite of this one, for example. The larger the 2 will be negative. So 10x is larger size than 2x, so the 10 gets a negative, and the 2 gets a plus. So that is the fully factored version of this quadratic. Make sure you attach the first factor, of course. And there we have it, fully factored form. Fully factored form. I keep crossing my F's. Do it one fell stroke. There you go. Fully factored form for h of x, and then we are good to go. Could we have been more efficient than that? Yes. There's one more rule. There's one more small algorithm that you can learn, barring fancier algorithms. The ones that you can use something called Descartes' rule of signs. I'm not going to go over that too much. Maybe I'll just go over it. You know what, let's go over it. I'm sorry. No, I'm sorry. Sorry yet again. I am not going to go over Descartes' rule of sign at the moment, because I feel that's just inundating with too many information. I'll just try to introduce it organically the next time I do another problem. Okay, but we have fully factored form, so we are done with h of x. So that's nice. Okay, so we can move on to doing the pre-written problems that I have. So first problem, we have f of x is equal to our favorite types. There's a 1 coefficient in the front. Those should be your favorite types of problems. Or let me rephrase that. There should be your least hated types of problems. They tend to be the easiest. Look how nice these numbers are. It's a 1. -5, -2, and +24. Not too many factors with 24, and there's only a factor of 1 unique factor for the first coefficient. So that's nice. We don't have a very large snowballing of values. So that's my quick survey. Let's get to the 0 candidates. What are the factors of 24? 1 and 24, 2 and 12, 3 and 8, 4 and 6. Those are close. So we don't have any other factors. Perfect. Factors of 1, easy, just 1. Because it's 1, I'm just not going to write it. I'll put plus or minus in front of these candidates. Which candidates are best to test first? Never pick the extreme numbers first. So I'm going to cross out 24, cross out 12, cross out 8, cross out 6. So again, because these numbers aren't very large, you have a very low amount of snowballing. So just pay attention to the first ones. Start from here, proceed in that fashion, and you usually can't go wrong with that idea. So let's start with +1 as a candidate for our zeros, as a 0 candidate. Let's copy paste this. 1, -5, -2, and 24. So running through the algorithm, summate straight down, product, sum, product, sum. It already looks wrong. Product. Yep, we get a remainder. We get a positive remainder. So this is not a 0. Let's try the other one, -1. So copy paste these exact same things. Or, if you're writing this on paper pencil, you could just simply erase this one. Save a little bit of time. But make sure you write down that you tried +1 already. And +1 did not work as a 0. So drop that. Product. Sum. Product. Sum. Product. Okay, that's clearly wrong. It's a positive value. So unfortunately, they both ended up being positive. So that's not going to help our case. In terms of intermediate value theorem. So we need to have a different guess. Let's try 2 as a 0 candidate. We're going to do 1, -5, -2, 24 yet again. So drop that. Product, sum, product, sum, product. What do you know? It failed yet again. This is a positive result. So should we check? What should be our next check in terms of what to test out? Well, 1 has failed, -1 has failed, 2 has failed. They all produced positive values, so I'm going to just keep moving to the right by picking 3 as a value. Let's pick 4. Let's see what happens when we pick 4. I think that might lead us to something useful. No, let's pick 3. I'm sorry. Let's pick 3. So if we choose 3, we'll populate this chart yet again. So drop product, sum, product. Oh, this looks like it could be something. -8. Oh, good. Thank goodness. So 3 times -8 is -24. Summate those ones 0. We have found it. All right. Congratulations, everyone. Mission accomplished. So we have a 0 right here. Which means what? The fact that we have a 0 means that this 3 here is a 0. And because 3 is a 0, that implies that x minus 3 is a factor. Don't forget this thing right here. That's a quotient. That's the leftover factor that we probably need to further factor. But what is this junk here again? We divided x cubed successfully by something that contains x with an exponent of 1, which means that this leftover thing is a quadratic. So it's 1x squared minus 2x minus 8. At this point, please use your quadratic factoring algorithm rather than continue on with synthetic division. So let's do it. So x minus 3. What are the factors of -8 that add up to be -2? It's -4 and +2. So x minus 4 times x plus 2. So quick check, -4 plus 2x gives us -4x. Yes. And also triple check, Positive 2 times negative 4 times negative 3 gives us positive 12. Positive 24, which is consistent with this one. Because again, that's how the distribution should work. All the constances should multiply to become that last term. The constances should multiply to become the last constant. The only constant, I mean. And then all the leading x's should multiply to become this 1x cubed. Yeah, they do. So we're probably good with this answer. So good to go. And then we are done. But let me go over what happens if we had chosen positive 4. I want to show you the intermediate value theorem in action yet again. So pretend we did not do 3 first. Like, what if we did not choose a 3 candidate? What if we wanted to try a more extreme value like 4 or even 5? Let's pick 5. So if you had chosen 5, let's copy paste the rest of this stuff. I want you to see how the numbers will quote unquote snowball. So you drop the 1, 5 times 5. 5 times 1 is 5. Summate. Product. Okay, so it didn't snowball very much in this example. Okay, that's fine. And then product. That's unfortunate. That's a positive as well. Okay, well, I was hoping that it would be illustrative of the remainder factor theorem, but we end up with a positive number, so it's not remarkably helpful. For choosing the 5, let me choose the 4. So am I trying to force the usefulness? Kind of. I had already forgotten the actual zeros for the problem. So there actually might be a 0 between the 5 and something else. But hold on, let me choose 4 again. Let's see what happens. Drop the 1. Product. Sum. Product. Sum. Oh, because 4 is also a 0. Yeah, well, that's spectacular. So that's why the 5 failed, right? So the fact that we tried a 5 as a 0 candidate produced positive. Just not the best situation. So, or unless I screwed up the mathematics somewhere along the way. I don't think I have. Yeah, okay, so that's just kind of a funny situation. So, again, we saw that no, x minus 2 is not a 0. So x minus 4 is a 0, because that's what we found here. I mean, x minus 4 is a factor because 4 is a 0. And then the other one we got was 3. Yeah, x minus 3 was a 0, and the last one was x plus 2. Yeah. Okay. So unfortunately, this is not illustrative of the intermediate value theorem because there's a lot fewer candidates. So we don't have to worry about as much nonsense. But we are done with this particular problem. Again, that's the answer right there. So not too bad. All right, let's do another one. So we have g of x. G of x is equal to. This is our least hated types because it has coefficient 1. It makes things a lot easier. All right, it's our favorite 24 from before. So products of factors of 24 will get us our 0 candidates because this one is just 1. So what are the candidates of 24? Again, you can just kind of steal this from the previous one. Strive for efficiency. Those are our zeros. To show full work, you would have to put them over 1, and then you have to put plus or minus. But anything divided by 1 is itself, so plus or minus over these things. Alright. Again, pay attention to the coefficients. It's 1 to 1, negative 14, and negative 24. So not tremendous values. So we're going to aim for the lower end numbers. Don't pick 24. Don't pick 12, nor 8, nor 6. These are probably our best candidates going from left to right. Let's pick something more intermediate this time. Let's pick 2 as our 0 candidate. Copy paste the coefficients or extract the coefficients to populate your synthetic division chart. There it is. And usual procedures. So product, sum, product, sum, right? Yeah, and then product. That's unfortunate, but we have a negative situation, so this one can be informative if we have some other sample data to go off of, testing data to go off of. So we'll set this aside for now. We just know that positive 2 as a 0 does not work, so x minus 2 is not a factor. I'm going to keep repeating that, I'm sorry. So let us test negative 1. So I picked something farther out. So if negative 1, after doing this indirect division, if we get a positive value, that implies that there is a 0 between positive 2 and negative 1, guaranteed by the intermediate value theorem. So let's test. Starting over all over again. So I'm going to keep saying this: drop, product, drop, product, drop. Okay, this is not right. So product, positive 14, sum is negative. That is unfortunately not that informative. So we have a 2 and a negative 1. They both produce 0. So to guess a 0 candidate between those is not super useful. So too bad. So could we potentially pick 1? Yes, we can potentially pick 1, but because it's not guaranteed by the intermediate value theorem, I'm not going to test positive 1. So I'm going to test instead positive 3, and hopefully that gets us somewhere useful. So 3 as a 0 candidate, starting over yet again. First guess is always the worst guess. So 1, product, sum, product. Oh, that's already bad. Product, sum is a negative value. They all end up being negative. Let me consult Descartes' rule sign real quick. This is positive, positive, one sign change. We have one sign change. That means we're guaranteed one positive answer. Oh, we have one positive answer. Let's test 4. I know I said I wouldn't use it, but pretend you didn't see that. So let's try 4. As a 0 candidate, going through the motions yet again. At this point, it should be ingrained in your brain. Perfect. Oh no. Oh yeah, that's good. That's good. That's good. That's good. 4 times 6 is positive 24. What do you know? Thank you, Descartes' rule of sign. So I chose 4. Well, to be fair, that's like the only positive left anyway. We would have naturally drifted towards that. Or maybe I would have picked negative 3 as a candidate. But picking 4 as a 0 candidate yields 0, so therefore 4 is a 0. Therefore, x minus 4 is a factor of g of x. Nice. All right. At this point, the 1, 5, and 6 is a resulting quotient that is a quadratic. Again, this is just x squared. This is positive positive 5x, and then this is just constant 6. So the quadratic is here. Use your favorite factoring algorithm. They're both positives. So 6 breaks down into 2 and 3 because positive 2 plus positive 3x gives us positive 5x. Combined with the 0, x minus 4 is a factor. Therefore, this is the fully factored form, the FFF of g of x. So we are finished with this particular problem. Wonderful. Let's do 2 more with very nice coefficients in the front. You know, the one with x coefficient 1. So now we have g of x. It's going to be x cubed plus 3x squared minus 18x minus not our other familiar friend, it's minus 40. What do you know? It's not 24 anymore. Too bad. But this is still coefficient of 1. Well, there's the factors of 40. There's a lot more. Try to have some sort of semblance of order, please, so you don't accidentally skip. But for the most part, again, the extreme numbers you will almost never use. That's all. candidates for 1. That's easy. It's just 1, but I ain't going to write it. I'll put the commas just to have some good form. Alright. So those are our candidates. Again, don't try to pick those ones. These are typically the wrong ones. Maybe 8, but the numbers, taking a quick survey, they don't steamroll very much. They don't snowball very much, so probably not 8. I'll go back to 8 if I really need to, but let's start from left to right. Picking positive 1 first. No, let's pick negative 1 first, arbitrarily. So negative 1 as a 0 candidate. Here comes the population. Populate, populate, populate. Yes, you have to write the coefficient right there. All terms must be accounted for, even invisible terms. More on that later. So drop, product, sum, product, sum. No, we're not quite there. Oh, how unfortunate. Product. But even then, this is informative because we have a negative answer. That means negative 1 is not a 0. So let's try positive 4. Let's try positive 4 as a 0. Alright. Drop, product, sum, product. Oh, that's good. Yes, 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 yes. Negative 10 per. Oh, no, positive. I'm sorry. Got too excited. And positive 40, what do you know? Summate that is a clean 0. Nice. So again, if we had gotten a positive value as a remainder, there must lie between x and 4 and negative 1. There must be another number that produces a 0. But since we actually gotten 0, that means that 4 is a 0, which means that x minus 4 is a factor of polynomial g of x. Perfect. This is just a quadratic, so please treat it as such. Factors of 10 that produce 7 is just 5 and 2. Easy. And we are done with g of x. Very good. Wait, which? Minus 40. Yeah. Okay. This is the last one where we have a nice clean coefficient of 1 in the front. So going back to h of x, we are going to have x cubed, 36x squared, minus a very unfortunate 157. 157x plus 120, and that is the problem. And unfortunately, 120 has a lot more factors, so 1 and 120. Does it feel useful to write out 120? No. It's probably not a 0, but I'll have to write it out to show full credit. 1, 2, and 60 makes 120, 3, and 40, 4, and 35, and 24. What else is there? Let me check this real quick. 5. What factors make up 24? It's 3 and 8. Oh yeah, we can play around a lot more with that, unfortunately. So we have 6 right here. So 6 and 5 times 40. I'm sorry, 5 times 4 is 20. So 6 and 20. And we have yet more factors that lie between these. So 6 is the higher up, and then 8 is the next number. So 8 in conjunction with 5 times 3 is 15. So 8 and 15. Next number up from 8 is 12. So this is 12 and this is 10. So 10 and 12. And 10 and 12 are so close together. We have gotten all candidates. So let's close this up. Clean this up. So unfortunately this is kind of a mess, but plus or minus. This is all over 1, which again, I ain't gonna write it. I'm not gonna put commas this time either. So one of these candidates should be our starting one, but the question is, which one shall we start with? Probably not these ones. They're too large. Probably not 15. Probably not even this. Probably not even these two. But Don't count them out just yet. So let's pick a 3 one, since these numbers go up to 157, which is pretty bad. So let's try positive 3 as a 0. So we have 36, negative 157, 120. That's really, really clunky. So drop, product, sum. Wonderful. We love these. This is 40 times 3, which is 120, but you don't have 43s, you have 39 3s, so take away 1 3. That's 117. That looks kind of clean. So summating that is negative 40. Hey! The luck of the draw. Sometimes the RNG giveth, sometimes it taketh. We're at 0. Perfect. Which means 3 is a 0. Perfect. Which means x minus 3 is a factor. The remainder, not the remainder, the quotient. This is the remainder, right? This is the quotient that follows. This is x power 1. This is x power 2. This is x power 1. If you don't see a sign, it's a positive sign. So there it is. What does this factorize into? This is just a 40. What factors of 40? Negative 40 make 39. That's pretty nice. It's x plus 40 and x minus 1. Because this is positive 40. This is negative 1. Summation of which is positive 39. It's too nice. Sometimes you get really lucky, and then sometimes you get really unlucky. And you just hope that your teacher doesn't give you an absurd number combination to work with during your test or something, because that's just an unfortunate nightmare. So the 120 is done. And I know I said that that'll be the last one where the leading term has a coefficient of 1, but there is a special subtype I wish to visit. So here it is. We're going to do q of x. Q of x is equal to x cubed minus 1. Alright. This is referred to as a difference of 2 cubes, but don't worry about it. The naming, this has its own special algorithm that if you memorize it, you can be very fast. But it's such a specialized tool, and I generally hate specialized tools. And my roomie can attest to this. I really, really don't like specialized tools. So let's stick with the current algorithm that we have, which is just basically synthetic division, which can be supplemented with intermediate value theorem and then the Cartwright sign. So let's do that. This one is actually very few candidates. We have a candidate of 1 and negative 1, right? So what are all the factors of negative 1? Just 1. Factors of 1, just 1. So we only have 2 0 candidates, 1 and negative 1. Wonderful. Which one is right? So let's try positive 1 as a candidate first. And this is the wrong way to do it. So we're going to take 1, take negative 1. Again, this is the wrong way to do it. Drop the 1, sum. Oh, it actually works out. Okay, but unfortunately, it's wrong. But I guess this is not the right example to show it. But you're going to have to take my word for it that this is wrong. Okay? You know what? You don't have to take my word for this. In fact, we can show that this is wrong. So we get a remainder of 0, which means that this one is a 0, which means x minus 1 is a factor. And remember what this is. This is the leftover. This is the quotient, right? So we start off with an x cubed. So therefore, this should be x squared with nothing else, right? And then if that is an x squared, then these two multiplied together should take you back to q of x. And you will see it doesn't lead back to q of x. It leads to x cubed minus x squared. Huh? Where's the minus 1? And where did this one come from? It's clearly not represented there. So what gives? So coincidentally, this one actually is the 0. Right? Well, maybe you don't know that quite yet. I'm just showing you that this leads to an erroneous conclusion. So unfortunately, something is wrong. And I'll just tell you what has occurred. Basically, we have an error because we have not accounted for all the spacing, which might sound weird, but essentially what's happening is the synthetic division is a super algorithmic machine, number crunching machine, and it is one of those machines where you have to put something into every space available to keep the alignment for the machine in order for the machine to work properly, because if things are misaligned, it will lead to weird results. And what I mean by that is there are invisible terms for x cubed minus 1. The first term, the leading term, is 1x cubed, yes, but you technically have an x power 2 term. It just has a 0 in the front. So this one, you have to place it into your machine. And the same is true for 0 times x power 1. This one is for x power 0. So all in all, there are 4 terms that you have to use to populate your synthetic division number crunching machine. So when you do the 1 as a 0 candidate, yes, you put the 1 here. But there are 2 zeros you have to mechanically put here and here. Because again, this is an algorithm machine. And if you don't populate it properly, if you misfeed the machine, it will lead to bad situations. Alright, so this is a negative 1. So let's see what's supposed to happen. So you drop this one here, and then you multiply. Sum, multiply, sum, and then multiply. Sum, finally we get 0. So this is the true result. This one is therefore a 0. Therefore, x minus 1 is a factor. What is this junk? That's the quotient. This is the dividend, or I don't know the terms. I think this is the divisor, and then this is the quotient, so this is the dividend. But this one itself is still a polynomial. Remember, it's x squared, x power 0. So we're going to take this one and multiply it to our known factor of x minus 1. So x power 2 plus x plus 1. Because that was there, this one is represented here, and this one's represented there. So this looks awfully long for something so short right there. So let's use distributive property just to verify it, because I think it's worth verifying this. So we have a 2 by 3 distribution, so just have good bookkeeping skills. Well, first to last. Finish with that one. And then second times first. Second times second. Second times last. You can see that these ones are opposites and therefore will cancel. So cancel, 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 cancel. The remainder x cubed minus 1, which is consistent with the original problem. So there it is. Alright. So we have verified through distributive property that this is the current product. I'm sorry, not the product, the current factorized form of q of x. Can we go any farther? We have a quadratic here. Let's use the discriminant test to see if it's... You know what? Let's not use the discriminant test just yet. This has 1 coefficient, so 1 and 1, 1 and 1 from here. So using any sort of combination, can we get a 1 coefficient in the front? You can kind of see no, because it's just going to give you 1 and 1x and 1x. And in no way can you produce positive 1 from 2 1s of the same signs that are both positive. So this is a non-factorizable situation. Let's double confirm it with discriminant test. So this is from the quadratic equation. The discriminant test here is going to be b squared minus 4ac. Again, this is a. The coefficient 1 in front is an a. The coefficient here is a b. And then this 1 is the c. So everything is just 1. So let's plug it in to our discriminant test. So 1 squared is 1, minus 4 times 1 is just minus 4. We're going to get square root of negative 3, and we cannot take a square root of a 3 to get a real solution. So therefore, this one has no real other factors. So we are done until you get to imaginary numbers. Well, let me show that. So that was the, again, we got a square root of a negative value, which means there's no real solution to this particular quadratic, which means this quadratic is not factorizable with real numbers. So that means this that we have here is in fully factored form. So that was just a tangent. When you don't have enough terms, you actually have invisible terms that you must contend with. So moving on, as promised, we're going to get to the leading term that has a coefficient that's not 1. So going back to f of x. F of x is equal to 2x cubed. So this one is still not that bad. It's just a coefficient of 2, which means there's only 1 and 2 as candidates. So minus 27x squared plus 93 minus 40. All right. So that's our situation. Let us first consider the factors of negative 40. Thankfully, it's not another 120, so it's not the worst. That's it for that one, and then factors of 2, 1, and 2. I'll put commas just to clarify. So again, any of these number combos could be one of our zeros. So 40 over 2, which is 20. 20 is a candidate. 10 is a candidate. 5 is a candidate. 1 over 2 is a candidate. Negative 1 over 2 is a candidate, so on and so forth. So take a quick survey of the numbers. We have 2, negative 27, 93, and negative 40. So probably not extreme values like 40, 20, 10, or 8. Probably. But I feel safe crossing out those 3. You don't have to cross them out, but I wouldn't try it from this end. So start from the lower number end. Maybe pick a 2 or pick a 4 or something like that. So let us choose 4 and see what happens. So 4 is our 0 candidate. Let's populate the chart. It's going to be 3, exponent 2, 1, and 0. So no invisible numbers to keep track of. So 93 and negative 40. Okay. This 93 is fairly large, so I feel confident picking this 4. So drop, multiply. Sum, multiply. Again, 20 times 4 is negative 80, but we don't have 19 fours. We don't have 24s. We only have 19 fours. So if 20 fours make 80, we just need to take a 1 4 to get 19 fours. So it's going to be 76. So negative 76. So summate that one. That already looks kind of bad, unfortunately. This is going to be a positive 17. You multiply those two. That is kind of a gross number. 68. Positive 68. If you summate that, we get a positive result. Wonderful. So 4 has failed us. We have a positive value. This can be informative. We'll save it. We'll save our work. Oh, well, I will shrink it. Moving on. Let's pick another one. Maybe. Let's see what happens. I just want to see. I want you to see what happens when we pick an 8, a relatively larger sized number. So if you pick 8, what happens? So we're going to use those numbers to populate. And just execute the steps as usual. Sum, product, sum. Wow, that is a large-sized positive number, relatively speaking. So fairly large. So I'm not going to pick any value between 4 and 8, since it's not guaranteed by intermediate value theorem, because this is positive and this is positive. There's no solid evidence that we have a 0 between them, but it might exist, but we're not guaranteed it by intermediate value theorem. So let's just set this aside for now. So let's pick negative 8 again, just to illustrate the point. So if we had chosen negative 8, what will have happened drop 2, product, sum. That looks kind of bad. And then multiply that. Ooh, I really don't want to do this. So I'm just going to qualitatively do it. We're going to get a large size negative. You summate, it's still going to be negative. You multiply gives you a positive. Ooh, we might have to do it. Okay. Looks like we have to do it. I don't think it'll work though. So this one times this. Wait a minute. Oh, I think I was mistaken. This one times this one gets us a large sized positive. So when you summate, this is a large sized positive. When you multiply, that's a large sized negative. So summing negative to negative gives you a large negative. You see how I didn't have to exactly crunch the numbers? It's just like a quick qualitative assessment. But we have a negative. What does that mean? Because negative 8 produced a non-zero and produced a large sized negative, and the smallest positive produced a positive, therein, between those two, there must be a zero candidate that actually produces 0. Again, guaranteed by intermediate value theorem, which is easier to show once we get to graphing why that works. But for now, just be satisfied with the fact that we do have a 0 between 4 and negative 8. Again, I picked negative 8 just to illustrate a point. I probably would have picked like negative 2 as a better candidate. But let's pick negative 2 now. So negative 2, starting over yet again. I really hate this 93. Alright, drop the 2. Product. Sum. Product. Ooh, that's going to be bad. But it will be informative. Because when you multiply those two, you're going to get a large size positive value. And then you summate those ones, and that's a whopping 155, which multiplied to a negative gets you a large size negative, which means that this is a large size negative. So this is not a 0. But because taken in with this piece of information that produced a positive value, then between negative 2 and positive 4, there must be a 0 guaranteed by remainder factor theorem. I keep saying remainder factor theorem, sorry. I mean intermediate value theorem. Intermediate value theorem. So not remainder factor theorem. Remainder factor theorem is this thing. Since we have a remainder that's not 0, that means this is not a 0, which is not a factor. So that's, which means x plus 2 is not a factor. That's remainder factor theorem. Or if you plug in negative 2 into this function and it spits out a negative value, that means it is not a 0. So, but I keep bringing it up. I keep confounding this thing with the other thing because they're so related. They're related in the same scenario. Whoops. Okay. So going back just a little bit, again, this 4 candidate has failed but produced a positive remainder, and then this negative 2 has failed and produced a negative remainder. So between those two, there must be something that actually produces 0. So what's between negative 2 and positive 4? Unfortunately, there's a good number of candidates. There is still negative 1/2, negative 1, positive 1/2, positive 1, and positive 2, positive 5/2, and then that's it. So we still have 6 candidates between negative 2 and positive 4, which is not the best thing. It's the perks of the digital medium. I'm going to keep this work, but I would just shrink it to a very small size. So we'll keep that just in case. Most people would erase it, but I typically would advise people to not erase it. Just start a new scratch paper. If you're doing this on the test, hopefully your teacher gives you scratch paper. Okay, so we have this. Because this is kind of a wide gulf, let's pick halfways between. Because once you pick half, and this is negative, for example, that means you can narrow it between this one or this side. So this is like moving the goalpost. So if we pick this extreme value 2 in this relatively to this range right here, and this one ends up with a positive number, you still have 5 candidates to check. So trying to be as efficient as possible, you would pick one of these 2 middle ones, and if that one produces positive, that's informative. This means that your actual 0 is either -1 or -2. If you pick 1/2, for example, and produce negative, that implies that your zeros are somewhere here. So that's why it's good to pick the intermediate values right here. So I'm going to pick positive 1/2 as our candidate. 0 candidate, and then we're going to copy paste the coefficients. So drop that product, sum, that's looking pretty good. Product, yeah, I like how this -3 ending works with this to produce 0. That's usually a good sign. So summate those two, we get 80, and of course, half of 80 is 40. Summate, we get 0. Perfect. We are good to go. That means that this is a 0, which means x minus 1/2 is a factor. This is a fractional situation, but I see these are all even numbers. So if we factor out 2, we're going to get positive 1x squared minus 13x plus 40. And we could take that 2 and multiply it to here just to clean it up. Factorizing x squared minus 13x plus 40. Factors of 40 that produce 13 is 8 and 5. Signs are the same. Both signs are negative. So yeah. Not too bad. Oh, I picked a -8 instead of a +8. Well, it is what it is. Here we go. This is what we have. Fully factored form. Yes. So FFF. Perfect. That is the fully factored form of f of x. All right. So moving on, we're going to do like 4 more, and that should be it for this situation. We have new problem g of x. You know what, let's do m of x, just for funsies. M of x. This looks like slope. Maybe that's not the best. Let's do n of x. Alright. Nobody writes O of x because it looks like 0. Yeah. So n of x is equal to 4x cubed minus 24x squared minus 43x plus 105. The 105 is gorgeous. Perfect. And then this 4 here is obnoxious. It's a 4. What are the factors of 105? Because we need to generate candidates. Let's do a factor tree real quick. Or whatever you call this. I don't know what to call this. The hockey stick thing? Alright, let's see. 21. Oh, that's not too bad. 3 and 7. It felt worse than it really was. Set that aside. So what are the factors of 105? We got to play around with these ones just a little bit. So 1 and 105. The next smallest one is 3. So 3 times the other factors, which is 5 times 7. So 35. So 3, the next number up is 5 right here. So 5 times the other 2 combined, which is 21. And the next number up is 7. So 7 and the other 2 make up 15. So 7 and 15. And I don't think there are any other factors. Yeah, because the next number up, 7, is 3 times 5, which is 50. Yeah, that's it. So let me delete this work. Let me just shrink it. Yeah. Here are all the candidates for 105. We got to find the candidates for 4. 1, 2, and 4. In terms of the unique factors. plus or minus. So there are a lot of candidates, right? I think using permutations, combinations, or whatever, we have 1, 2, 3, 4, 5, 6, 7, 8. We have 8, and then there are 3. So what is it? 8 times 3 is 24. 24, and then it's plus or minus. So 24 times 2 is 48. But some of these numbers are redundant because I think some of them are redundant, right? Oh, I don't think any of them are redundant. Oh, interesting. Because 5 over 2 is distinct from 5 over 4, and none of the top numbers are divisible by 2. Oh, so we actually do have, what did I say, 48 answers? I mean 48 candidates, but remember, not all candidates are equal, so probably not that, probably not that, probably not that. Or maybe 15 over 4 might work. So let me not scratch out anything, but it's probably not 105 in any sort of combination. Alright, so we have all those things right here. Take a quick survey. It's a 4, negative 24, negative 43, 105. It doesn't look tremendous snowballing in terms of the numbers. I'll pick something intermediate like 3. 3 is a 0 candidate. So we have 4, negative 24, negative 43, positive 105. So check the degrees. 3, 2, 1, 0. So we're not missing. We don't have any invisible terms to account for. So drop the 4. Product, sum, product. Oh, that's not good, right? Sum. Product is a negative 21-ish, so that's a large size negative. So when you summate those, you're not going to get 0. You can get kind of a negative value right here. That's from the 3. So I'm going to move a little farther up. I'm going to pick positive 7 as a candidate because we got this negative here. So picking a 7, let's see what we get using the synthetic division. So let me cheat a little bit using Descartes' rule of sign. We have 1 sign change, 2 sign changes. Ooh, that means that we can have 2 positive zeros. I'm sorry, yeah, 2 positive numbers that are zeros, or 0 positive numbers that are zeros. Okay, that's not tremendously useful. Maybe the opposite. Let me see something. Negative, negative, positive. Ooh, we were getting 1 negative value. I should pick negative values instead. That's okay. I already committed to the 7. So let's drop the 4. 28. 4. 28. 17. Negative 17, right? No. Negative 13. 15. Yeah. And then multiplying those ones. Does that actually work? Wait. 35. Yeah, it actually works. Well, what do you know? The luck is on my side for this problem. Perfect. Okay. So somehow I got lucky with the 7. It wasn't 100% luck though, because again, I chose not to pick the more extreme values. I saw that the 3 produces a negative value, so I picked something farther up, which is a 7. So not 100% luck, but a high degree of luck. Because 7 produced this, because the 7 candidate produced a 0, that means 7 is a 0, which means x minus 7 is a factor. What's left over here is a quadratic. Using your favorite factoring method, we shall factorize this. But I'm going to use my favorite factoring method. So this 4 here consists of 1 and 4, or 2 and 2. The 15 consists of 15 and 1, 3 and 5, and that's it. It's probably not this one. Probably not this one. So let's check. This is a 6 and this is a 10. Yep, sure enough. So the 2's are the coefficients for the x terms. And since this is a 2x and this is a 2x, it doesn't matter how we put the 5's and the 3's. So 5 and a 3. The 2 signs are different, and the larger of the 2 products is positive. So then positive goes on the 5, negative goes on the 3. Copy paste this factor. So at this point, I believe we are done. Yes, yes. 10x minus 6x is 4x. Yeah, it's confirmed. So we are good to go. This answer is good. And just using a little bit of a remainder factor theorem, this one means that the 0 is negative 5 over 2. So if we plug in negative 5 over 2, it should produce 0. If it truly is a 0. Yeah, that should make sense. Something that is a 0 for a function will produce 0 if you plug it in. So I deliberately chose an obnoxious negative value that's also a fraction. So let's see what happens. So what is negative 5 halves cubed? It's negative 125. Oh, maybe that was too ambitious. Over 8. And what's this one squared? It's positive 25 over 4. That's still a 5, negative 5 over 2. Everything else is just copy paste. So it's times 4. So this one is that one. This one is this one. This one is that one. That's still 105. So is it equal to 0? That is the question. So distributing that is 6. 6 times 5 is 150. That's an obnoxious number. Yeah. I'm going to go ahead and change this to denominator 4. So this 430 over 4 to match with this one. This is positive 105 still. And then cleanup step. Hopefully we get something nice. Oh, I think I screwed up the number somewhere. Let me double check. 5 times 5 is 25. 25 times 5 is 125. Yes. 5 squared is 25. Yes. And then I really hope I didn't mess up something. It looks like I did, though. Somewhere along the way. Wonderful. 6 times 5. Yeah. 2 times... No, 5 times 43 is 215. 215 times 2 is 430. Yes. Okay. Alright, well, continue on with this particular line of work. We're going to combine the fractions first. We're going to produce 305 over 4. That's really bad. And then we have this one plus this one, which gets us negative 45. This is supposed to produce 0. It doesn't look like it produced 0, so I messed up something along the way. Maybe... It's hard to evaluate where things have gone wrong. I do believe these are the zeros. Why do I think that? I don't think I messed up this part. And I don't think I messed up this part. So I think it's the plug and chug that got messed up. Probably. If you're a VOD user, you just skip this portion. I feel like this isn't going to be that useful. I'm just trying to illustrate remainder factor theorem. But it seems I've stumbled on some difficulty. Why now of all times? I think I used up all my luck in the previous problem. No, I used up all my luck finding this particular 0. That's what happened. Well, let's evaluate. 2015. I have a feeling this is messed up. 200 plus 15. Yeah, that's correct. Ooh, this is bad. Well, I'm going to have to check the distribution for this one real quick. This is just a 2 by 3 distribution, so it shouldn't be that bad. So first one to first one gives us 4x cubed, and then first one to second one. Sometimes you just gotta check, and then this one times this one. So we're done with the x, and then the negative 7 times the first. And then negative 7 times the second. Finally, last one times last one. 7 times 15 is 95? Yeah, 95. That's... Is that correct? No, not 95, thank goodness. 70 plus 35 is 105, okay. So the 4x cubed is consistent with this one, yes. That's a negative 24x squared, yes. This is a negative 43x, yes. 105, yes. Okay, so the factoring, the fully factored form is correct. That means my plug and chug is incorrect, but let me check my 0 first. So manually set 2x is equal to negative 5, divide by 2, x is equal to negative 5. Yes, that's supposed to be the 0, so that's correct. Which means my evaluation is incorrect somewhere along the way. So let me delete all this clutter. Oh no. Keep that. Delete that. I'm going to delete all of that. Okay, that's all gone. So again, the idea is this 0 that we can get from this factor is negative 5 over 2. That means if we plug in negative 5 over 2 into n of x, then it's supposed to produce 0. If it truly is a 0, it should make 0, right? That's the namesake. So let us check the evaluation real quick. So I'm just going to plug in everything. I'm going to actually fully write it out because I fear that I've made a mistake, a very ridiculous mistake somewhere. Yeah. I really don't like this part. So question mark 0. Alright. So evaluating this cubic portion, 5 times 5 is indeed 25, as said before. And then 125 times 5 is negative 125. Yes. And then 2 cubed is 8. Our familiar friend from logarithms, or exponential scenarios. Alright, this one right here is going to be positive 25 over 4. This remains a negative 5 over 2. So let us copy paste everything else. That's still times 4. This is still times 24. This is still times negative 43. Well, I really don't like that. And then this is still plus 105. Is it really 0? Let's see. 4 partially cancels with the 8, thereby producing a 2 on the bottom. And then this one... Is that what happened? Did I forget about this term? I think I forgot about this term. Yeah, okay, I think I found the mistake. This one I just forgot to write it in the previous. No, I didn't, because I canceled the 24 with the 4. Yes. So that should leave us a negative 6 times the 25. I'm going to finally write it out. Yes. And then this one right here is positive 5 times 43. It's 20 plus 15, 200 plus 15, so it's 215 over 2. Positive because the negatives cancel. We have a plus 105. Yikes. Oh, this is a 2. That is a 2. I think before I had a 4 here, right? Yeah, okay, so that was the issue from the first check. Okay, good. So now that this is over 2 and this is over 2, we can summate those and we can summate those ones, and hopefully this is going to be good. So summating those two, the 5s will cancel, and then the produces 90 over 2. which is 45. And summating those two, we will produce, this is 150, negative 150, so we produce negative 45, right? Yeah. And what do you know? This positive 45 is opposite of negative 45, thereby producing 0, so we have confirmed it using plug and chug. So because we produce 0 by plugging in negative 5 over 2, we verify that negative 5 over 2 is a 0 independently of this thing right here. So that seems like solid evidence. But we've already checked it by fully distributing it. So it is a very robust answer. Wait, what problem was this? 105. Okay. Alright, so we are going to have 3 problems left. And of course, it just gets progressively more annoying. So now we're going to get p of x. Back to p of x. P for polynomial x. Uppercase for no reason in particular. And that is equal to 45x cubed plus 111x x squared and 11x. What's with all these ones? And then we have minus 7. So polynomial right here. I do want to briefly mention this is a cubic function. Cubic functions go from downwards negative infinity to positive infinity, since it's a positive leading term, which means you're guaranteed to cross the x-axis at one point, so you're guaranteed one real solution whenever you're dealing with odd-powered functions. So if you set a equal to 0, you're guaranteed one answer if this is odd, ignoring all the other ones. So this is, if this had been x to the power of 31, and this is equal to 0, you're guaranteed one solution. So if this is like 53, that's an odd leading degree, leading degree, which means you're guaranteed 1, 0. So that's pretty nice. You don't need to memorize that though. I just felt like mentioning that in brief. So here we go. Factorize this one and factorize this one to generate our 0 candidates. So factors of 7, 1, and 7. That's very nice. Factors of 45, not terrible, but not super nice. So 1 and 45. 45 consists of 5 times 3 times 3, so the next number up is 3. 3 and what? 3 times 15. Next number up from 3 is a 5. 5 times what? 5 times 9. And I think that's all we need. 15, we already have 15. 9, we have 9. Yes. So those are all our candidates. Plus or minus. Alright, well, take a quick survey. We have 45, 111, 11, negative 7. So kind of quote-unquote largish numbers in comparison to typical problems, typical starting problems. So we're going to pick maybe... Oh, we all have all our zeros are fractions, unfortunately, which is why I made this problem, right? Okay, so I deliberately put a 45 in the front, and I put a 7 in the back because now we have a bunch of fractional zeros just to work with not so nice values. But no big deal. Don't be intimidated. It just has to do with fractional work, which could be tedious. It is tedious, let's be real. Well, let's not rotate. Let's not get rotated on that one. Alright, so we have this one. Which candidate should we use first? Let's use something that's easy to work with. There are no good answers. Let's just pick 1/3 arbitrarily. Positive 1/3 as our first 0 candidate. Take all the coefficients, make sure that everything is accounted for. We have an exponent 3, exponent 2, 1, 0. So no invisible terms. So 45, 1, 1, 1, 11, negative 7. Alright. Time to slog through the mathematics. So drop that. A third of that is 9 times 5, 3 times 5 is 15. Yeah, it's 15. And then summate. That is looking bad. You see how this is a large positive number? This is positive, so this is going to be positive. That's going to be positive. That's going to be positive. And I think the end, it's going to be positive. But it is... we must follow through with it, unfortunately. So summing up those two, we're going to get 126, which is divisible by 3. So let's sum product, multiply that out, divided by that is 42. Yikes. Summing that is 53, which is not divisible by 3. Wonderful. So negative 7 is negative 21 over 3. So as promised, the end sum is a positive number. Therefore, 1/3 is not a 0. Therefore, x minus 1/3 is not a factor. Okay. Too bad. Such is life. We move on. Alright, so 1/3 did not get us a 0. So where do we go from here? You can try 7. You could try something like 7 over 9, but let's not do that. I'm going to try instead... let's try 1 over 9. Negative 1 over 9. Arbitrarily. Okay, so if we're picking that one, then the rest of this will be populated in the exact same fashion. Here we go. Drop that. Multiply that. So we're going to get a negative 5. Summing that, we get 106. Is this divisible by 9? It is not. So we already know the answer is going to be wrong. Once you get not divisible by the fraction, the numerator, once this is not divisible by the denominator, then you're going to keep getting a bad fraction. And in the end, this is going to be a fraction. So when you summate that, you're not going to get 0. But should we follow through? Yes, because we might be able to use it in conjunction with intermediate value theorem. So I'm going to just approximate this as negative 1 over 10 just for faster mathematics. So we're going to get close to... oh no, we can't because it's too close. Okay. Well, I will approximate it though. So this thing divided by 9 is close to 1 point... well, no, 10. I'm sorry, 10 point what? That's negative 90. No, 11. It's 11. Yeah. Negative 11, thereby leaving us with what? 7.7-ish. Okay, so it's basically, it's a larger sized value than 11. So the answer here is going to be negative. So when you multiply, it's going to be a small negative, and when you multiply by a fraction, it becomes even smaller. It's a very small positive. So when you summate that, that's a negative answer. So that's why I followed through, because plugging in this, checking this as a 0 candidate produced a negative remainder. This one produced a positive remainder. So according to intermediate value theorem, we have a 0 between 1/3 and negative 1/9. Okay. I'm going to cheat using Descartes' rule of sign. This is no change, negative change. So one sign change means we have one positive value. So I'm going to pick a positive fraction. Again, don't worry about that. It just helps me narrow down the candidates just a little bit. Not tremendously. I'm going to pick 1/5. Positive 1/5. Alright. So yet another slog through with the numbers. So 45, 111, 11, and negative 7. I think there's a slightly more efficient algorithm, but I don't think I've ever learned it. So if you know a better algorithm, use that one. So drop that. Product. Yeah, sum. Product. That's going to be 24. Summate that. Oh, that's perfect. Yes, 35. Product is 7. Perfect. Summating that, we get a remainder 0, which is exactly what we want, which means this is a 0, which means our factor, one of our factors is x minus 1/5. It's a fractional situation, so we could probably steal a number from here. Yes, this is divisible by 5, divisible by 5, divisible by 5. So let us factor out the 5. Steal that 5 and multiply to this one. Okay, remember this is a quadratic. Because this is exponent 3, and we divided by this one, so all the exponents will downtick by 1. So this is exponent 2. Alright, so divide by 5 is 9x squared. Divide by 5. What was it again? I have to redo it, I'm sorry. So 24, yes, 24x. Divide by 5 is 7. And again, we steal that 5 and multiply it to this one instead to get a nice clean answer. This is a quadratic. Is it a factorizable quadratic? Is the handsome question. So avoiding the discriminant test, I'm just going to try it out real quick. So we have 9 and 1, 3 and 3. We have just a 7. That's easy. 7 and 1. So can we produce a 24? Yes, this is 21 plus 3 is 24. Perfect. So clean it up. This cleans up into 5x minus 1. This one factorizes again into this one. So the 3x has to be multiplied to a 1. They're both 3x's, so it doesn't matter. And then the second 3x has to be multiplied to the 7. Both signs are the same, and then they're both positives. And we are done with the problem. Should be good. Very sloppy test. Let's do 5 times 3 times 3, which is 45x cubed. Which matches with this one, yes. And then again, sloppy test is negative 1 times 7 times positive 1, which gives us negative 7. That's an ending, it's consistent. And with the lazy check, it seems legit. So, P of x is done. Wait, which one is it? It's the one with a bunch of 11s, okay. Let's do another one. 2 more problems to go. Alright, here we go. Starting off with, let's do z of x. That's weird. Nobody ever uses z, I think. Maybe because z is reserved for one of the axes, z-axis, perhaps. So we have a problem of negative 12. That's obnoxious. 12x cubed plus 77x squared minus 162x. And then plus 112. The problem with later math is that it's hard to come up with good problems on the fly. You have to pre-plan things. Alright, so that's what we have. It's rather unfortunate. This is a negative 12. This is a 77. This is a negative 162. This is a 112. So we have some obnoxious candidates probably. This is not an even number, so you can't factor something clean from all of them, unfortunately, I don't think. Yeah, so this consists of 2, 2, 3. This consists of 7, 11. They share nothing in common, so it's not even worth checking the other two. So we cannot factor something from all 4 terms. This is a cubic function with a negative, so it goes like something like this if you know how to graph it, which means we're guaranteed 1, 0. Using Descartes' rule of sign, we have a sign change. That's 1, sign change 2, sign change 3. So we're guaranteed 1 positive 0. Positive number that is a 0. Yeah. The 0 is neither positive or negative, you know. Alright. So, again, don't worry about the tests that I've performed, but if you do know how to use those tests, go ahead and use them. Alright. Let's start getting our candidates. So we have 112, which is very sad. What do we have here? We have 2 goes into 112. 556. Oh, that's very unfortunate. That's a 7 and an 8. That's a lot of combos. And then here is the 12, which is 1, 2, 3, 4, 6, and 12. That is unfortunate. But I've written the problem, So now I gotta do it. Alright. All the factors of 12. Well, start off with the 1. The first easiest number is 2. Next number up, there's no 3's, but there is a 4. So these two make 4, and then the rest of them is 7 times 4, which is 28. Oh, I should put the other one. So 1 corresponds with 112. And then 2 corresponds with 8 times 7. I'm just trying to go in some sort of semblance of order. Now, some people just willy-nilly just try to list off starting from left to right, and then some factors you can miss those ones if you're not careful. So we're going to have a 4, and the next number up is 4 times 2. No, the next number up is 7. So 7 with 8 times 2, which is 16. And I think that's it. For the value... No, we have 8, because it's 8 times 14. Almost missed it. I think that's all. Yeah, because we have a next number up. There are no 9's, no 10's. There's a 14, but this is already here. Okay, good. So all the factors of 112 should be accounted for if I wasn't too sloppy. And these numbers, which should take those perks of digital medium. Right here. Alright. Close parentheses. So those are all our candidates. It's a lot. Imagine doing this for like a degree 5 polynomial during a time test of like 20 minutes. It's a nightmare. And I don't know why some people still do it. Okay. Let me take a quick swig. Okay. Where do we even begin? The numbers look kind of large-ish. So, probably picking an 8 is a good idea. But I'm going to be lazy and pick a 4. Because 4 is easier to multiply out. Alright, so we have a negative 12. Make sure all the numbers are accounted for. This is a 3, 2, 1, 0. Yes. No invisible terms. Because again, your synthetic division algorithm is very, very mechanical. All terms must be present. Drop that. Times. That is a 29. Yeah, 60. Yeah, and then multiply. We don't have 30 40s. We only have 29 40s. So minus 1 4 is 116. Sum. It's going to be, ooh, I can't do this in my head for some reason. 6 and 1, 4, 46, negative 46. Yes. Multiply that out. We did not get lucky, unfortunately. Alright, so 4, 2 plus 16 is 18. Negative. But the result is negative remainder. This is not a 0, so x minus 4 is not a factor. Okay, but this is still informative, so let us take this, shrink it, and move it to the side, as it deserves. Alright. 4 did not work as a 0. It got us a negative result. The negative is fairly large. It's like negative 60-ish, close to negative 60. So, what happens when we pick like a negative 1? Let's do 1 divided by 1 with a negative. I just want to see what happens. So negative 1 as a possible 0 candidate. So populate the old chart. Drop. Product. Sum. Product. Oh, that's bad. That's bad. That gets us an even larger negative value, so we're gonna get. Oh, wait a minute, wait. I take it back. That gives us a large size negative indeed. So we're gonna get 251. But multiplying by a negative gives us a huge positive. So this is a big positive. When you summate, it's a big positive in the end, which is good for us. Which means there is a 0 Because this is a positive remainder, this is a negative remainder, then, according to intermediate value theorem, there lies a 0 between -1 and 4. Is that really useful, though? We do have a bunch of fractions. That's okay. Shrink it and put it off to the side as it deserves. I remember saying that we're guaranteed one positive number that is a 0 because of Descartes' rule of sign. Again, one sign change, two sign change, three sign changes, so we could have 3 positive candidates, or we could have 1 positive candidates. But because this is an odd degree, we're guaranteed 1 positive. Perfect. Again, just to stress, don't worry about that test. Okay, but if you know, you know. So next one up, we're going to try +2 instead. Let's see where things go from here. I don't think it's going to be the right one, but maybe. So drop that product. Sum is 53. Yikes. And 106. No, that doesn't look good. And then we get, or maybe it is, 50, -56. You know what? That's good. Oh, thank goodness. So multiply that is -100 and -12, so -112. Perfect. Sum is 0. What do you know? So 2 worked out. So 2 produces a 0, so therefore 2 is a 0 of z of x, which means x minus 2 is a factor of z of x, which means this is a quadratic leftover, which we can factor using our favorite factoring methods. So let's take this, put it on the side, and then take this, extracting the quotient, which is useful for us. We have negative x squared plus 53x minus 56. Those are kind of large size values, which is unfortunate. There's a negative in front of the quadratic. I don't like negatives in front of the quadratic, so I'm going to factor out the negative from here, because my factoring algorithm doesn't take negatives very well. So I'm going to use factorization. 56, close parentheses. I'm going to take this x minus 2 and eat it. And we'll multiply right here. Yes. This one's not so useful anymore. I'm going to shrink it and put it off to the side. So here's our current work in progress. It's looking pretty good. It's just this is kind of bad. So factors of 12 go in order. That's it. Factors of 56. 56 consists of 8 times 7. Oh, that's a lot. So 2 times 28. 4 times 14. And then 7 times... Oh, that's it. That's not too bad after all. So which of those possibly produces a negative 53? In the middle, they're both negatives. I mean, yeah, they're both negative terms. So 16 and 48. No, that's not. That's a 63. Very close. This is a 32 and 21. So 32 and 21 is 50. Yes, it must be that combo. So 4x has to be multiplied to the 8, which goes here, and then the 3x has to be multiplied to the positive 7. I mean, I'm sorry, to the 7. They're the same sign. They're both negatives. Copy paste that first factor that we found via synthetic division. And we should be done with this problem. Let's do the quick sloppy check. So this one times this one times this one is going to give us 12x cubed, which is positive. Oh, see, this is why it's good to check, even with the sloppy method. We forgot the I forgot the negative sign. Whoops. So let us remember how I factored out the negative because I didn't like it, and I subsequently dropped it by accident. Now it's back. All right, let's test that again. So negative times x times 4x times 3x gets us negative 12x cubed. Now that's consistent. Good. Then the negative times negative 2 is 2. Positive 2 times 56 positive is 112. Yes. So with a quick sloppy check, it seems that this is good and this is good. So the rest of them should ideally fall in place, right? Is that a dubious check? Maybe. It's good enough for now. Alright. That's it for z of x. Which brings us to the final problem of today, or right now. Which is, let's go back to f of x. Full circle. Back to f of x. So f of x is dreadful 168. Wow. X cubed plus 211x squared minus 109x plus 10. Yikes. That's bad. That one's not so bad. So factorizing 10 is just 1, 2, 5, and 10. Easy. It's this one that's disgusting. So 168 consists of 4. So 2 times 2 is 4. How many 4s fit into this one? It's going to be 42. Yeah. 42 consists of 7 times 6, which is 7 times 2 times 3, I think. Yeah. So that's fully factored for 168. What are the candidates? It's going to be 1 and 168. It's going to be 2 times the rest of this junk. So 21 times 4 is 84. 2 and 84. Next number up from 2 is 3. So 3 times the rest of this junk is 56. Next number up is 4. 4 times 42. Getting closer. Next number up is no 5s. There's a 6 here, so 6 times 28. We've run out of space. Does it feel extra to write out all those factors? Again, it kind of is, because most of the time, especially with these small numbers, you're going to get pretty nice answers. Quote unquote, nice answers. Because for the most part, most teachers won't give you terribly obnoxious problems. And if they do, I feel sorry for you. So we have next number up is 7. There's a 7 here, so 7 times 24. I just made extra space and now it's gone. Next number up is 8 times 21. I hope that's the last one. No, it's not. Next number up, there's no 5, so you can't make 10. We can make 12, though. Wonderful. So this one is 12 and 14. Okay, that should be the last one. 12 and 14. Again, we typically do this if your teacher requires you to show all the candidates for the zeros. Incredibly tedious. Pardon me as I beautify this real quick. There you go. I took up too much space with this 3 and the 4, right? It's the struggle. Okay. Try not to waste too much time on this. Alright, last resort. I'm just gonna put a big chasm between the 7. No, I'll put it right here. Yeah. Thank you, digital medium. Here we go. And then I'm going to deliberately move the higher numbers off to the side like so. You know what? Yeah, it's fine. Like this. Alright, so that Herculean task is done. Let me shrink it. This one we don't need anymore. Okay. Let's see. Big number, big number, big number, small number. Using Descartes' rule of sign, there are two sign changes, so I should probably start with -0 numbers that are candidates. Anything else to make a comment on? You're guaranteed one solution. So if we do the negative version for Descartes' rule of sign, we have one sign change. Yeah, we're guaranteed a negative value, so let's start with the negative values first. I'm thinking about whether or not I should explain Descartes' rule of sign. Nah, too bad. I think when I do a marathon of a bunch of factoring problems, ranging from quadratics to exponent 4, degree 4, or degree 5 polynomials, then I'll mention Descartes' rule of sign in brief. But for now, I'm just going to mention in my own head. So, there we go. We should probably pick a larger size negative value, so I'm going to pick -5, and I'll hope that that's going to be a good zero candidate. Ooh, that's going to be multiplied to 168. Let's pick -1. Yeah, it probably won't work, but the results will be informative, because I don't want to deal with -5 right off the bat. So let's populate the chart, make sure all the numbers are present. This is 3, 2, 1, 0. Yes. To 11, -109, and then +10. So drop that. So you see, this is why I did not pick 5, because it'll be annoying right off the bat. So some product. Summate that one. My brain can't process this one. It's 53, yes. Right? No, 43. Right? Yes. Okay, yeah, confirmed. And then this one times this one is a -43. It's not going to give us the right answer already, but let's follow through. So -152, which multiplies to become a big positive. This is a big positive. Plus 10 is still a large size positive. So 1 has failed us. It is not the right. It is not a 0. It has been eliminated as a 0 candidate. So we got a positive remainder. So let us keep track of this. Shrink it. Put it off to the side. What now? We should probably pick a larger size negative value. I guess we have to resort to 5 at this point. So -5. No. Let's pick a fraction instead. Let's pick -1/2. Yeah. I'd rather work with 1/2. Wait, that's not going to work. Okay, so I'm kind of cheating a little bit by dropping this down. If you multiply by -1/2, that's going to be -84, which if you add those two, it's going to give us an odd number ending, and that's not divisible by 2. So that is not the best candidate. So let's pick 8 plus 16 is 24. Let's pick 1/3. Let's pick -1/3. Yeah. Alright. So picking -1/3, because again, the -1/2 looked like it was going to result in a bad situation. So I'm going to switch at the last moment to -1/3. So starting off with 168 to 11. -109. 110. So drop that. Because again, I know this is divisible by 3, so multiplication. We are going to get 56. Summating those ones, I hope it's a good number. We're going to get, what are we going to get? We're going to get 5, which is the 11, and we get 15, yeah. Yeah, this is definitely divisible. No, it's not, because 1 plus 5 plus 5 is 11. It's not divisible by 3, unfortunately. Ooh, this is a unfortunate situation. So if we multiply that, we're going to get -50-ish. Summating that, we're going to get -160-ish. But I'm going to cheat and make it 161. Again, I'm just trying to get the rough estimation to get this final remainder. So multiplying those ones, we're going to get negative 50. Why did I choose that? Okay, negative 50-ish. So when you summate that, it's going to be a negative answer. So again, I just want to see the overall situation. Okay, so negative 1 as a candidate gave us a positive remainder, so it's not a 0. And then this one as a candidate gave us a negative remainder. So therefore, according to intermediate value theorem, we have a 0 between negative 1 and negative 1/3. That's nice. So let us shrink this. So let us take a quick survey of all the numbers between, all the candidates between negative 1 and negative 1/3. So what do we have? So negative 1 and negative 1/3. What's between those ones? So we have why is this difficult to do in my head? This is negative 30, negative 0.3-ish. This is negative 1. Alright, so negative 1/2 is going to be between, yes. Do we have anything else? Technically 5, 6. Oh, there's a lot of them. So we have 2/3. Goodness gracious. We have 5/6. Negative 5/6 is 1. 5/7. Yeah, it's not tremendously useful, but 1/7 as a candidate is probably not good. What is 1/7 of 168? Right? It is 24. Okay, so it might work without doing anything else, right? Do we have any other candidates? We have 10/24. Let's just pick one of these. Knowing my own brain, I probably pick one of these as a 0. So this one, this one, or this one. But understand that there are actually many more candidates. So try to pick the intermediate one. I'm going to pick negative 2/3 as a candidate, because at least we can eliminate the ones to the left of 2/3. Negative 2/3. So picking negative 2/3. Or eliminate to the right, depending on what we get in the end. So 168, drop that down. This is 211. 109 and then 10. So multiplying those two, the product, this gets very annoying, of course. What's 1/3 of 168? It is 56. But 56 times 2 is 112 with a negative. Yeah. So summing that, we get 9. Is it 99? No, it's not 99. It's 89, right? Yeah. 89, I think. Let me double check. No. It's actually back to the 99. Yeah. Because if you steal 1 from here and you place it here, it's 100. And then 100 plus 111 is this. Yes, that's correct. So that is positive 99. It is divisible by 3, thankfully. So we get negative 33 times 2 is negative 66. I really hope this is correct. So summating those two, we get 175. Is this divisible by 3? I don't think it is. No, it's not. This is 12. 12 plus 1 is 13. 13 is not divisible by 3. It is a tragedy. But it's okay. Continue on as much as possible. If we pretend this is negative 177, this is divisible by 3 as an estimation. This one divided by 3 is 59. 59 times 2 is close to 120, so 120-ish with a positive. So we end up with a positive value in the end. That is not a 0. What can we figure out? Well, since this negative 2/3 gives us a positive, and this negative 1/3 gave us a negative. That implies that our answer, one of our answers is between, one of our zeros is between negative 2/3 and negative 1/3. Thank you, intermediate value theorem. That's the most I can get out of this information, so let me shrink it and put it off to the side. Now we ask ourselves, what values are between negative 2/3 and negative 1/3? .63-ish, .33-ish. I'm really bad with fractions at this point. Well, 5/14. I'm kind of cheating a little bit because I know I would not pick 5 and 14 as a potential candidate. 2/7. That might. What is 2/7? Is that between here? I think it is. So cross multiplication, we have 7 and 6. Yes, and cross multiplication. We're dividing by a larger number, so it's smaller size than this one. Okay, yeah. So negative 2/7 is a candidate. I can see myself making this as a 0 for this problem. So again, I'm kind of cheating it a little bit. Problem maker's privilege. So let's try negative 2/7 as a 0. So we're saving the best problem for last. So 168, 211, negative 109, and then 10. So drop that. What's the product of that one? Well, 168 divided by 7 times 2, right? So 168 divided by 7 is 24, with a negative times 2 is therefore negative 48. Yeah, summating those two, we're going to get 3, that makes the 11. We need 100, so that's 63. That's a positive, perfect. Thank goodness that's divisible by 7, right? So 63 by 7 is 9. 9 times negative 2 is negative 18. I really, really hope this is it. So we have negative 127. Is that divisible by 7? It is not. Okay. Well, it's unfortunate. So multiply this times this. We're going to get... What are we going to get? Positive 1. 57 is 8. Closest is 8. 8 times 2 is 36. So it's close to 36-ish. So it's a positive-ish 36. If you summate that, we end up with a positive value. What does that mean? Yet again, this is not a 0. It gave us a positive remainder. But we've narrowed the search a little bit more because, again, the negative 1/3 got us a negative remainder. So, thanks to intermediate value theorem, between those two values, there must be something. There must be a 0 candidate. No, there must be an actual 0 that produces... There must be an actual number that produces a remainder of 0 between those two. And unfortunately, my fractional skills are not that good, so shrink that. That's the most we can get out of this situation. Alright, you can see the pain of dealing with these type of problems, right? Okay, so let's take a quick pause for a moment. I'm going to actually use a calculator because I don't want to do division by 7s because you get really bad repeats. Alright, so negative 2/7 is like negative 0.28-ish. Wait a minute, maybe that's why things went wrong. I should not pick this one. Alright, so negative 1/3 is negative 0.33, 3-ish. Yeah. I actually picked something to the right. I didn't pick something to the left, unfortunately. Okay, well, we can proceed in two ways, right? So we have a negative 1/3, and then we have a negative 2/3. And that's very interesting. Because what that means, this one resulted in a positive remainder, this one resulted in a negative remainder, and this one resulted in a positive remainder. So that means we can narrow our search between here and between those two numbers. So we actually have two candidates now, two zones to check for candidates, because I mischose this one. I was supposed to choose between here, and I thought this number was between those two, but apparently I can't do math. Alright. So we have two zones to check. So which one shall we check? I think I'm biased towards this side for reasons, right? So what number is between negative 1/3 and negative 2/7? Negative 2/8. No, that's not right, because that's negative 0.25. So negative. I wish I could do math better. So 5/8. That is what, 0.325, I think. Let me cheat by using a calculator. No, it's way off. It's negative 0.625. You know what? That's the other candidate. So this one is between those two. So since it's between those two, and I've just found it, let's try this one as a candidate, right? Okay. I really hope this is the last one, because at this point I may be losing your interest. That's okay. I will live with that. You could probably, if you're a VOD, well, you must be a VOD watcher if you're watching this. So let us hope that this is the final one, please. Alright, let me shrink this box a little bit. Here we go. Let's hope for the best. So drop the 168. Product is 21 times 5 times negative 5 is 105. Summating those two is 106. Is that divisible? That's not divisible by 8. Oh no. Okay, well. I am getting impatient, so let's multiply this using a calculator, unfortunately. I wish I could show you more tricks, but for sake of expediting the process, we're going to get this. Which, if you summate it to negative 109, you're going to get a whopping negative 175.25 divided by 8 times negative 5, which gives us negative 400-ish. So this is a big negative value. We summate that one, that's a negative value. So this results in a negative value, which means that we have a 0 between those two. So we've narrowed the goalpost yet again. But are we truly happy? We are truly not happy. Shrink this. The only question is like whether or not I did the mathematics correctly. Let me check something very quickly. Otherwise it could lead to an unfortunate situation. Okay, yeah, the 66.25 is correct. I was wondering if that was maybe a mistake, but it is correct. So now we need to find a negative value between negative 2/3 and negative 5/8. Because again, this one produced a negative remainder. So our 0 must be between negative 2/3 and negative 5/8 as a candidate. So what do we do? Do we have a 16? No, we don't. So what number is between those two? something smaller than that, so negative 5 over 7. Do I dare? Yeah, let's pick that one. So negative 5 over 7. I'm hoping this is the last one, right? I feel like this problem has dragged on unnecessarily long. So we have 168, but you could see the pain of such a problem type. So we've already done this before, right? So 168 divided by 7 is going to be 24. And then the 24 times the 5 gives us 120. But it's a negative times positive negative. Yes. So summating that one, we have 80, 91. Yeah, 91. Yes. Yeah. Oh, thank goodness, that's divisible by 7. So 91 is divisible by 7. So we escape slightly. So 91 divided by 7 first is 13, and then 13 times 5, negative 5, is negative 80. Alright, summating those two is negative 189. I really, really hope this is divisible by 7. Is it divisible by 7? I'm going to use a calculator because I'm getting tired. It is. Oh, thank goodness. So 189 divided by 7 is 27, and then 27 times 5, please, is not what we wanted. Well, that is unfortunate. So that's a big negative sign in the end. I should have known, because this is close to half. This is over half, and over half is like negative 90-ish. That's over negative 90-ish, and we're still getting a negative answer. Okay, so that means we have yet narrowed it ever so slightly. So the answer, the zero candidate, the zero that's supposed to be there is now between those two. So take this one, shrink it, and toss it to the side. Just like my time. So there it is. So what is between those two? So we have to find something smaller than 7. It's 6. So let us try negative 5 6. Yeah? Yeah, okay. So if you so the reason being, if you take a 5 and you divide by 7, it is a smaller size than 5 over 6. But that's for sizing, that's magnitude. But if you put a negative on a larger magnitude, then that is a smaller number. So that's between those two. So this has got to be the right number. I have a good feeling that negative 5 6 is the correct zero. I'm almost willing to bet money on this. So we have 168, 211, negative 109, and 10. So please work. We have 168 divided by 6 is 28. 28 times 5 is 140. I'm going to cheat it using a calculator, so it's negative 140. Summating that one is 71, right? 1, 2, yes. Right? Yeah. Okay. And this is not divisible by 6. Oh no. Oh no, 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 no. Okay, fine. Well, this is suffering, right? Mathematical suffering. So 71 divided by 6 times negative 5 is like negative 60-ish. Alright. Well, we have to continue on with the math so we can narrow things down just a little bit more. Okay, let me double check my work to make sure I didn't do any ridiculous mistakes. So we have negative 169-ish. So times 5 divided by 6 gives us a positive 141-ish. Hey, summoning those ones, we get a positive leftover. So remainder is positive. We finally hit the other side of the wall. Okay. What does that mean for us? It means our answer is between -5/7 and -5/6. Because again, these two zero candidates, what did they do? This one results in a positive remainder, and then this -5/7 resulted in a negative remainder. So we finally hit the other side of the wall. Let us shrink this. So we're very, very close to finding the 0. Alright, but now comes the tedious task, the arduous task. What's between -5/6 and -5/7? That's hiding within our candidates, right? And unfortunately, I don't have a good eye for these things. So let me delete this first. So let us take this and put it here. I'm not going to go in the other route. I'm already committed. Too bad. So what's between here? Well, 5/6 is approximately this. And then 5/7 is approximately that. So we just need to find something between those two. -0.75. Do we have a 3/4? No, we don't. All right. I'm running through the possible candidates that can maybe work. What's 5/12? 5/12 doesn't fit between those two. No. It's over half. So I need to pick a value over half. 10/14 is 5/7. No, we already have that. 5/7 is, we already have that. I feel like I missed something. 10. No, 10 doesn't work. 5/7 doesn't work. Shucks. We have 2 1/2. No. Again, I'm just running through this. Like, what number is between those two? Because we've narrowed it down. And here's the tragedy that might have occurred. I hope it has not occurred. But this -5/7, if this has been a pause, and this search is in vain. So let me check this work real quick. Yes, negative. This is positive. This is negative. Yes. That is negative. This is... Oh no. I think I've just confirmed my worst fears, right? Yeah, the sums to be a negative, right? But then we have a negative times a negative. This is positive. This is positive. That means this is positive. Oh no. Wait till you get to matrices. Or if you've already done matrices, you can see that's probably like the worst thing in terms of having small mistakes propagate into big mistakes. Okay, so here's what's going on. Okay, there was a mistake here, which means that the goalpost that was moved was a mistake somewhere along the way. So moving here was a mistake, right? Yeah. Thankfully, there's a semblance of order. This is how we progressed. First candidate, second, third, fourth, and then 5th, 6th, 7th. So we should have stopped here between. So our answer is between this one and this one. Again, hopefully I did the mathematics correctly. This is a negative. That's a positive. This is a negative. This is a negative. Negative times negative is... Oh, this is also a mistake. So negative times negative is positive. Ooh, yikes. So let me delete these two prior work. These later subsequent works. Okay. Which means, since this is still a positive and this is also a positive, that means our answer lies between those two still. This is... a big waste of time. You know, this is like watching one of those people play like a Souls game, right? It's like when you're watching someone play, I don't know, like Dark Souls 3 or more recently Elden Ring, right? And someone's fighting a boss, and then you keep making a mistake, and it takes like an hour or something to several hours to fight a boss. That's what's happening here. Like, we know how to do this. It's just like the technical aspects are just wearing down, maybe possibly due to fatigue. All right. So our answer is between here. I feel like we went forwards in the wrong direction, and now we have to walk backwards. It is truly a tragedy, a mathematical tragedy. What is this? All right. So our answer is somewhere between here yet again, and we know that this is going too far. So, wow, that is unfortunate. You see how these subsequent results are all positive? That means we're between here. Where's 2/7? So negative 2/7 is negative 0.28. This one resulted in a positive number. This one resulted in a negative number. This one resulted in a positive number. So again, we had two pathways to choose. This negative 5/8 is between these two. So this is not it. And then negative 5/8. That resulted in a positive number, right? Wait, does it? This is... I think I may have misevaluated this yet again. Okay. I think I misinterpreted this one. Okay, well, because this is on the right-hand side. I know I pointed it out before, but I think streaming for a long time has fried my brain. You know, it's the streamer debuff. Okay, well, that means I'm going to repeat my work. That's the worst thing, repeating your work. Okay. Can I escape this fate? You know what? Let's just go in the other direction at this point. Let's go here. I'm going to skip moving to the left. That seemed like a failure. So, new proposition. We're going to try to find the zero that's between negative 3 and negative 27 rather than go the other way, because the other way got all screwed up. Okay, so what value is between those two? I hope we don't have very many, right? So 2/7 and 1/3. So what's between those two? Well, is 5/8? No, we already tried 5/8 in the other direction, right? Yeah, that's not quite right. So we need something less than half. Yeah, but it's greater than 1/4. So let me think. Again, I'm trying to generate the candidates. 5/12 is what? That's too much. 5/7 is the other direction, yeah, 5/7. I think my brain truly is fried at this point. 5 divided by 28. That's definitely not an answer that I would use, and then that's also wrong. So 2 divided by 7. No, 2 divided by 6 is 3. No, so don't try the 2's. Let's try the... We have to try the 5. 5... Is it truly 5/12? No, that's too much. I already said that. 5/8 is also too large. It's only getting worse. 5/14 is past our range. 5/21. Do I dare? That's too small. Let's try the 10's, right? Ten over 42. It can't be 10/42, can it? 10/42. No. My skills are rapidly deteriorating. 10 over 21. No. Let me. I'm just thinking out loud. You don't have to forgive me. Let me kick. Maybe it's the lack of oxygen going to the brain. Okay, so let's take a quick pause here. I'm just gonna get up and move around, and hopefully come back with slightly more oxygen to my brain. So give me like 2 minutes. All right, here's the alternative hypothesis, right? What if, in designing this problem, I did a miscalculation? And then, subsequently, as a result of the miscalculation, I had written the wrong polynomial, thinking that it was factorizable. And what if I copied that, and it's now f of x? So that would mean that this is an improperly made problem. And if it's improperly made, then all this work is in vain. That is the proposition at this time. So I think for the sake of my sanity, I'm just going to run this into the calculator real quick. And if it works, then I will see the answer, and that is cheating, right? But I feel that I'm exhausting my brain power, sapping me of my strength, so it might not be worth it at this point. Oh, you know what? I actually generate this. Okay, I did not generate this problem by hand. Okay, I saw the answer. Whoops. What? It's negative 5 over 3? What? That means I messed up way far ahead. That's weird. Okay, so I've seen the answer. I've seen the light. Here is the answer. Okay. Because I'm getting tired. So we have 7x minus 2. 3x plus 5. And then lastly, 8x minus 1. Remember in the beginning, I told you that we were guaranteed one negative answer. This is the negative answer. That's the factor. Then the 0 is negative 5/3. And interestingly enough, that's nowhere near. That means I really screwed it up somewhere along the way. Well, that is the unfortunate situation. So basically, something got messed up somewhere along the way. So I think at this point this is correct, and I think this is incorrect. So let me check real quick. That's negative, and then this is positive. Yes, and this is negative. So this is negative, and this is positive. Okay, that seems right. That's weird. Okay, let me check this again. This is positive. This is negative. This is positive. It's negative, this is negative, this is positive. So this is correct. So this first work should be correct. Alright, because again, our answer is supposed to be negative 5/3. So this one should be correct by quick evaluation. So checking this one as well. That's a negative, this is a positive, this is, maybe this estimation is, that's why. You see how this is summing this up is a negative, and negative times negative is positive. I can't believe I did this mistake like 3 times. So this is actually positive 50-ish. So this is positive. And now, hopefully, you can see where the problem arises, right? You see how this is a negative 1, which is positive. This is also positive. So this is actually not informative at all. Wonderful. Truly, truly tragic. So this is negative 2 1/3. So for the sake of illustration, let me pick something like 5 negative 5 over 1. Okay, so if fate had changed, if I had chosen a different path and had instead chosen a negative 5 as a 0, I want to show you what happens, okay? Could you get bamboozled during a test? Yes. If this was on the test, I would have failed. I would have moved on, actually. No, I think I would be so stubborn in finishing this problem that I would just exhaust all the remainder of my time on the test. I would panic like midway through. I'd be looking at the clock and like, wait a minute, I shouldn't be stuck on this problem. And then that would be the end. Let's see. So 168 and then times the 5. Oh, that's really bad. I think this is why I didn't choose it. Because 5 times 168, according to my calculator, is negative 840. Summating that one is negative 629. The product of which is a very large positive value, right? It's a very large positive. You don't even have to do the math with this. Summating that one is a big positive value. That is a big negative value. Summating those, you have a big negative remainder. And from this result, you can see that this 0 candidate produces a negative remainder. So in conjunction with this piece of information, the answer should lie between the 0, a 1, 0 should lie between negative 5 and negative 1. And then you can see this one does lie between those two. Alright, so again, cheating. Because I looked at the answer, cheating. We know that the 0 is negative 5/3. So if we had chosen negative 5/3, you notice now I'm saying we, because I'm trying to absolve myself of responsibility. No, that's one of those key strats. If you don't want anyone to feel guilty, you make the group guilty. You make it as ambiguous we. This is one of those political office politics strats. Instead of saying I was wrong or saying you were wrong, you could say we were wrong. You can kind of spread the negativity, right? All right, so we have 168 here, or even like any sort of group dynamic. If you're doing a group project, and let's say you know someone screwed up, and it wasn't you, so someone in your group screwed up, and basically you lost all the data. If you wish to save that person who screwed up, you could say, yeah, we have made a mistake and we deleted the information by accident. So you would be saving the person. If you want to save yourself, you can also do that. But you should generally try to be honest. Okay. So dropping this down, multiplying straight across. What is that? Since I've already cheated this far enough, let's cheat even more. So 168 divided by 3 is 56. 56 times 5 is negative 280. So multiplying this one, it's negative 280. Let me put the rest of these numbers, of course. So summating that one's not too bad. Negative 69. Whoa, that's nice. Yeah, that's too nice. And then if we multiply that, that is going to be positive 115. Alright, summating those ones, we get positive 6. And here is the reprieve. So 6 divided by 3 is 2. 2 times 5 is negative 10. Finally. And it only came because I cheated. Wonderful. Yeah. So because this candidate produced 0, that means that this is actually the 0 of f of x, which means this translates into a factor of x minus 5/3. It's a fraction. Usually this gives you a clue about how to factorize this. Because this is a 3, we can change it to a nice scenario, nicer numbers by multiplying 3. But can we pull a 3 from those 3 terms? Probably. So factor out 3 from 168. We're getting 56. This is a quadratic, because this is only cubic. So divide by 3 is 23. Divided by 3 is 2. Alrighty, we'll distribute this 3 to those ones, giving us 3x minus 5. As promised. And then here, I'm not going to cheat any farther. Factors of this one is 56 and 1. 2 and 28. No more 3s, I think. This is a 5 times an 8. No, I'm sorry, 8 times a 7. Yeah, 8 times a 7. Next one is, therefore, 4 times 14. 7 is the next one. 7 times 8. And that's it. Those are all the factors of 56. Factors of 2, that's simple. 1 and 2. How do we generate a negative 23? They both have the same signs and they're both negatives. Okay, so this one times this one is 8 plus 14. Almost there. 8 times 2 is 16. 7 plus 7 is 20. Yes, so this is the right combo. So this one factorizes, therefore, into 8x times plus 8x minus 1, and then 7x minus 2. Because this makes negative 16x, and this makes negative 7x. In summary, that's going to be negative 23x. So that concludes it. So we have, as fully factored form, let me shrink this real quick. As fully factored form, we have the first factor, which is 3x minus 5. Second factor is 8x minus 1. And the third factor is 7x minus 2. So fully factored form for f of x. It was definitely a journey. I feel like I spent more on this problem than all the previous problems combined. Yeah, so that just tells you if you screw up one small calculation, like right here, the signage, it was like a signage issue, right? Then that would lead you astray, and then that leads you to the wrong pathway, and it only gets worse from there, because you think you're getting closer, when in fact you're getting farther. But that's the answer, fully factored form. Hopefully, it wasn't too bad. Well, it was kind of bad, right? Okay. That's that. Yeah, I think I'm going to call it, because I think my brain is fried at this point. It's been overclocked. You can see the steam rising on my head. Okay, that's it. I think next time I'm going to be covering more factorization when my brain is refreshed. We're going to do a mixture of problems. We're going to probably go over exceptional special cases of factorization, like a difference of 2 cubes, or a sum of 2 cubes, difference of 2 squares, classic quadratics, exponents, degrees beyond 3. That's the plan anyway. Alright, so at this point I'm going to call it. I will see you another time. I might not stream tomorrow. It's probably going to be... I'll try to stream tomorrow, but I don't think I'll be able to do it. Hopefully I'll stream sometime in the nighttime or sometime in the afternoon. Alright, that's it. Thank you for watching. See you another time.